good evening, depending on where you're joining us from. My name is Rosalba Rincon. I'm an associate editor for Batteries and Supercaps and ChemElectroChem. And together with my colleagues, Greta Heidenrich, as editor-in-chief of Batteries and Supercaps, and Kate Lawrence, editor-in-chief of ChemElectroChem, I'd like to welcome you to this virtual symposium, Beyond Lithium-Ion Batteries. This event is brought to you by Chemistry Europe, an association of 16 chemical societies from 15 European countries. And we've organized this together with Professor Ivana Hasa, who is here with us today. We have a really exciting program with 5 presentations on 2 different subtopics. So first, we're going to hear on sodium-ion batteries or sodium batteries from Professor Philipp Adelhelm and from Dr. Nagore Ortiz-Vitoriano. And then we're going to have 3 presentations on multivalent batteries from Giuseppe, Elia, and from Magali, Gauthier, and from Professor Robert Dominko. Before we start with the program, I'll just like to let you know that there will be time for questions after every presentation, so you can use the chat function to post the questions to the speakers. Please always mention the name of the speaker so we can monitor the questions. And also, if you have any technical issues, we'll be monitoring the chat and trying to help you troubleshoot with any difficulties that you have. But if you have issues overall and you cannot hear or see the presentations, this event will be recorded and all the participants are going to receive a link with the recording in the next few days. Okay, before I start, I'll also like to let you know that we are going to give a couple of announcements at the end, but if you cannot stay, please take into consideration that there's a special collection on this topic, and if you click on the top right corner of your screen where you see the logos of Batteries and Supercaps and ChemElectroChem, you can go to this collection and see the papers that have been published. So I'm going to introduce Professor Ivana Hasa. She's an assistant professor of electrochemical materials at WMG, the University of Warwick in the UK. After completing her PhD in 2015 on the design and characterization of sodium-ion battery materials at Sapienza University of Rome in Italy, she moved to the Helmholtz-Institut Ulm in Germany for a postdoctoral position working on post-lithium chemistries and on the investigation of structural and chemical composition of battery materials. In 2016, she joined the Lawrence Berkeley National Lab in California to investigate the chemistry and evolution of solid electrolyte interface for silicon anode materials. In 2019, she returned back to the Helmholtz-Institut in Ulm as a research scientist responsible of the sodium-ion group research activities. Finally, since 2020, Ivana joined WMG as an assistant professor, and her research activities are directed toward a fundamental understanding of the processes governing the chemistry of sodium-ion batteries. Okay, so without further ado, I don't want to take more of your time, so I'm gonna just give the mic to Ivana.
Thank you, Rosalba. So as you said, good morning, good afternoon, and good evening to everyone connected here today from all over the world. It is a great pleasure for me to be here and share this very interesting session. And thank you very much for the nice introduction. But as you know, today it's not about me, but it's about Beyond Lithium-Ion Batteries. And we have 5 fantastic speakers with us today. I would like to say before starting that given the unusual circumstances that we are all living today, this seminar represents a very great opportunity to catch up with the latest updates that we have, to keep exchanging knowledge, ideas, and discussion, which are the basic foundation of science. So I'm very happy to be here with all of you today. So we're going to focus on battery chemistries beyond lithium-ion batteries, which, as all of you know, represents maybe the most successful example of secondary battery, without any doubt. We all had a great celebration in 2019 when the Nobel Prize for Chemistry was finally awarded to Dr. Yoshino, Professor Whittingham, and Professor Goodenough for their pioneering work on lithium-ion batteries. But nowadays, we are also all witnessing at a continuously growing demand of lithium-ion batteries, and this fast growth calls for improvement in cell technologies, which are going to be able to satisfy all the different requirements according to the different application that we are interested in. So, as you know, the global demand is going to be around 1,000 gigawatt hour of batteries in 2025, and only the electric vehicle battery market is going to require about 400 gigawatt hours in 2028. So I guess there is plenty of work for us to do here, and we cannot rely only on the current lithium-ion chemistry to satisfy this huge demand. And that's why we are all much interested in sodium-ion batteries and multivalent chemistries, where other parameters rather than energy density, in which of course lithium-ion batteries are dominating, are very important, such as safety, cost, the sustainability, raw critical materials use, and the manufacturability. So in this context, the beyond lithium-ion battery chemistries may play a very important role, and they can also become the next generation sustainable batteries of the future. So we will start the session on sodium-ion batteries with Philipp, Adelhelm, and Nagore Ortiz-Vitoriano, as Rosalba mentioned before. And we will follow with the second session on multivalent systems with Giuseppe, Elia, Magali, Gauthier, and Robert Dominko. So I guess we can already start with our first speaker. Maybe Philipp, you can already start sharing your screen in the meantime that I'm going to introduce you. So as all of you know, Philipp Adelhelm is coming from Humboldt-Universität, Berlin. Philipp is a material scientist. He received his education at the University of Stuttgart and the Max Planck Institute for Metals Research. From 2005 till 2007, he was a PhD student at the Max Planck Institute of Colloids and Interfaces in Potsdam, in Germany, where he worked on carbon materials for energy storage in Antonietti's group. In 2007 until 2009, he was a postdoc at the Dubai Institute of Nanomaterial Science in Utrecht, in the Netherlands, in the Young's group, studying hydrogen storage materials. And from 2009 until 2015, he was a group leader at the Justus Liebig University Gießen in Professor Sianek's group, with the main interest was in exploring the cell chemistry of sodium-based battery systems. So from 2015 until 2019, he was a professor at the Friedrich Schiller University Jena. And since October 2019, he is a professor at Humboldt-Universität Berlin. And he heads a joint research group on operando battery analysis between the Helmholtz-Zentrum Berlin and the Humboldt-Universität Berlin. His main interests are on material aspects of rechargeable batteries, so lithium-ion, sodium-ion, and sulfur, as well as new cell concepts like solid state. So I will pass now the mic to Philipp, and please, we can perfectly see your screen.
Okay, thank you, Ivana, for this nice introduction, and welcome everyone. Good afternoon, and thanks to the organizers in trying out these new formats to distribute science around the world with this online symposia. So I hope this goes well, and hopefully you can all see me. And I'm happy to show you a few slides on research on sodium-ion batteries and some results from our own lab. So this is on sodium-ion cells and also solid-state batteries. So usually I start with the introductory slide, which shows you the, let's say, two most relevant parameters on rechargeable batteries when we talk about mobile applications. And this is, of course, energy by weight and energy by volume. And if you basically classify the technologies that we have, I think this is not a surprise. We know that lithium-ion battery is clearly ahead of any other technology that we have in terms of energy density. As Ivana already mentioned, there was a Nobel Prize given to the development of this technology, and we are very much looking forward on how this technology now is really boosting sales of electric vehicles. And the next market will be probably grid storage, and there are robotics and drones and 3D mobility and so on. So there are a lot of applications of batteries in the future. And of course, this comes with a discussion on the resources and geopolitical issues, and the question whether we have also sufficient materials around. So this is why people look for alternatives, right? And of course, you could think about being better than lithium-ion batteries in terms of energy density. Then you have to look at, for example, metal-air batteries, and we will see in a minute a talk by Nagore on metal-air batteries. Some other people focus more on developing cheaper batteries, so you're significantly better than nickel metal hydride or lead acid, but maybe not as high in energy density as lithium-ion cells. And this would be a classical example of sodium-ion battery technology. I also would like to show you this slide from Avisen Energy. So this is an agency monitoring the battery sales and the battery industry around the world. And if you see the forecast on how the battery market is growing in the next years, it's really dramatic. So this is why we have all these gigafactories that are being built around the world. And you can see here in blue, this is the electronic devices. This was the reason why lithium-ion battery technology became so important. But you can see already now the market is becoming very small compared to the other applications, especially right now the EV market. So we need a lot of more batteries and maybe not lithium-ion for everything. Sodium-ion batteries work essentially the same like lithium-ion batteries. So you can, in principle, use the same production lines as for lithium-ion batteries. You just change the materials. And of course, the ion that is traveling through your battery. So instead of lithium, you go to sodium. Instead of all these compounds that you see here on the right side for cathodes, so the well-known lithium cobalt oxide, the NCM materials, NCA, and so on, of course, you need a sodium version. And on the other electrode, you're looking for anode materials that work very well for sodium. Scientifically speaking, it's of course very interesting to compare lithium-ion and sodium-ion batteries because the sodium-ion is a little bit larger. And this can have benefits, but also drawbacks. And there's a lot of influence on the thermodynamics. So this means, for example, the cell voltage or the desolvation energy. But there's also like a lot of effects on kinetics. If you think, for example, of diffusion or the charge transfer and so on. And as mentioned, this can be always better or worse for sodium when you compare it to lithium. And discovering this is part of science, and this is something that we look also into in my group. If you want to read about sodium-ion batteries, there are many good reviews around. Maybe you also want to consider this one. This is very recent. This is something Ivana just put together with Montse Casas-Cabanas from CIC in Spain. This summarizes also a little bit the different approaches on sodium-ion batteries. So maybe you want to have a look at this review as well if you like. To make a long story short, if you compare sodium and lithium-ion batteries from a materials perspective, you have probably more options for the cathode materials because simply the chemistry is richer for layered oxides. So simply there are more compounds available. And on the other side, on the anode side, you probably will have less options compared to lithium-ion batteries. This is an overview of a map, let's say, showing the activities on sodium-ion batteries around the world, and there's probably even more. This map shows really just the companies, startups, or larger companies that work on sodium chemistries, so to say, for sodium-ion cells or also high-temperature batteries. And you can see that there's quite a bit in India, also in Asia, in Europe, and the US, and so on. And the nicest example right now is always the company Haina Battery from China, which managed actually to bring, let's say, have a prototype for an electric vehicle based on a sodium-ion battery and also a 100 kilowatt-hour stationary energy store. And this is basically a nickel and cobalt-free cathode material. So this is very nice in terms of abundance of elements. So no nickel, no cobalt in this chemistry here. All right, let's get a bit to the science part of sodium-ion batteries. And I think it's always very nice to look at voltage profiles because this is something that is very characteristic for a material. And voltage profile is full of information about how your material is storing sodium ions. And on the left-hand side, you see the comparison of lithium cobalt oxide in green and lithium cobalt oxide and sodium cobalt oxide. And you can see lithium cobalt oxide is a material that works very well also in application. And the reason for this is simply because you have a very nicely sloping voltage profile at high voltage, so around 4 volts, and in a very narrow voltage window. So most of the lithium ions are stored with the same amount of energy being released or being stored. And if you do the same thing for sodium, you can see the behavior is very different. So the capacity is comparable, but the voltage where the sodium storage occurs is a little bit lower compared to lithium, and also is distributed over a much wider voltage range. Okay, and there are a lot of steps in the voltage profile, which is in principle undesired, but which is the result of a lot of ordering phenomena in layered materials. And on the right hand, what you actually want to do is to get from such a staircase voltage behavior to a sloping one. And in principle, you also would like to increase the voltage, right? Because a high voltage is always good. The same thing can be actually seen for lithium nickel oxide and sodium nickel oxide in comparison. So also here in case of sodium, you have this staircase behavior. And in case of lithium, you have a largely sloping potential. So the question is like, how do we get from here to there? And in sodium-ion chemistry, we have quite a bunch of possibilities, and this means simply you can add other elements to your layered materials to tune the voltage profile. And this is what many people do. And I just show you one result from our lab. So what we look here is is a compound with a content of sodium 0.8, and then we have just iron and manganese as transition metals, and we intentionally also add some lithium. And the lithium is not sitting in the alkali layer, but the lithium here sits really in the transition metal layer, and this way actually stabilizes the structure. And as you can see here from the voltage profile, we don't have this staircase behavior anymore, so we have a sloping behavior. There's also a voltage fade and so on, so not everything is perfect. But you can see that by changing the stoichiometry of these transition metals and by adding elements like lithium or even magnesium, you can stabilize certain structures. Overall, however, the whole process of storing irons in these compounds is extremely complex. So you need many methods to study these materials, and still, even though you apply a lot of methods, very often it's not clear what really happens. This is a more recent example that we studied. So this is a sodium manganese nickel oxide, and again we add lithium as a stabilizer, but now half of the lithium sits in the alkali layer, so together with the sodium, and the other half sits in the transition metal layer. The lithium does not actually go out of the material during charging, so it really remains in the structure. But what happens actually during charging is that the lithium changes its location, so that the distribution of lithium ions in the structure changes during charging. And when you do charge this material, first lithium goes into the alkali layer to occupy empty spots, and if you do further charging, the lithium moves backwards again. So quite an interesting behavior, full of dynamics, so to say, and not very well understood. Another example is shown here for anodes. So now we go to the other side of the sodium-ion battery, and on the left-hand side you see a comparison of tin. Okay, so tin in principle works for lithium. Then you also get actually a staircase behavior, right? This is tin, and you see the voltage, the storage voltage or the redox potential for lithium storage in tin is around about 0.6 volts, which is in principle a bit too high. You would like to have it closer to 0 volts. And in case of sodium, you can see in this case you are more lucky, so to say, because you're closer to 0 volts, and therefore tin is a quite attractive material for sodium-ion batteries. On the right-hand side, you see a comparison of graphite. And graphite is a very interesting example because almost all lithium-ion batteries use graphite as anode material, because lithium forms this nice LiC6 intercalation compound, and this is shown here. So lithium goes into the graphite and lithium goes out. This all happens at around 0.1, 0.2 volts, so very nicely suited to reach a high energy battery. Unfortunately, for sodium, the capacity is 0. Right? It works for potassium and for other alkali ions, but not for sodium. So what we were wondering actually is whether you can still actually use sodium ions and graphite in sodium-ion batteries. So we came up with another approach that I will discuss on the following slide. So from the classical perspective, sodium ions alone hardly intercalate into graphite. So there are no so-called binary graphite intercalation compounds that are rich in sodium. And what we do instead is actually we intercalate this solvated ions, so the solvation shell along with the sodium ion. In a lithium-ion battery, you really don't want this because it leads to fast aging. But in the case of sodium, this approach is actually quite promising because it's highly reversible. Okay, so we intercalate not the naked ions, so there's no strip off of the solvation shell during charge transfer. We intercalate the solvated ion, which is of course much larger, but surprisingly works very well. And how well is shown here. So these are 2000 cycles, and you can see the capacity is completely constant. Also, the Coulomb efficiency is very constant. And on the right-hand side, you see the voltage profile. And we picked here several cycles. So this is the 5th cycle, 10th, and so on, up to the 2000 cycle. And you can see the voltage profiles are almost ideally matching. So even after 2000 times storing sodium in this material, there's no degradation of the crystal structure, which is, I think, quite remarkable because the solvated ions are very large. So the breathing of this graphite is actually quite strong. One drawback of this approach is obviously when you look at this value here, we are limited to around 110 milliamp hours per gram. Right? So this is not perfect for battery. We want to be higher. So we look for solutions in order to increase the capacity of these materials. One interesting thing about this solvated ions is that they actually can move very, very fast in graphite. So usually you would assume such large solvated ions, they are very slow because they are large and they cannot really move in the graphite lattice. But the opposite is actually true. They move extremely fast, and the diffusion coefficient is actually higher compared to lithium ions diffusing in graphite. So there's a lot of mobility in this material, and therefore the rate capability is very high. And this is shown here. So this is, for example, current density of 11 ampere per gram, and you can still see you get quite a decent capacity. Once again, for batteries, you want to be higher, so we need actually solutions to this. If you compare this to supercapacitors, this capacity is actually very, very high. So what we did actually in a study, we used this material also as an anode material in a hybrid ion capacitor, because here it works actually very well, and the capacity for supercapacitor is quite high. And this is what we did. So this is a study we published recently in Batteries and Supercaps. And what we did in order to increase the capacity, first of all, of graphite is we were adding tin. So this is a composite now containing 17 weight% of tin, and all the other stuff is graphite. And this is simply done by thermal treatment. So we take tin chloride as a tin precursor, heat the whole, mix it with graphite, heat everything up, and then you have tin distributed over your graphite matrix, so to say. And these are the electrochemical results. You can see here, this is actually a voltage profile which very much looks like tin. So most of the capacity comes from tin, and additional capacity comes from the graphite. And the graphite part is extremely fast. Okay, the tin part is a bit slower, but the graphite part is faster. And what you get here at a rate of C/10 is you get 220 milliamp hours per gram. The Coulomb efficiency in the first cycle is around 90%, which is very good. And this value, basically the first cycle Coulomb efficiency, is really important for application. So many materials that perform good have sometimes very low values, maybe 50% or so. And this means you cannot use it in a real battery. So this first cycle efficiency should be also as high as possible. And 90%, I think, is quite a reasonable value. If you do long-term testing over 2000 cycles, and here we went to a higher rate, and simply because otherwise the test would last very long, you can still see the material has a very stable capacity, and there's only a minor decay over so many cycles. Now let's switch to solid-state batteries. So we again have a look at the normal lithium-ion battery, and what people try to do nowadays is they try to replace the liquid electrolyte by solids. Okay, so you go away from all these organic solvents which are flammable, and you try to replace the liquid phase by solids, usually by solid particles. This can be an inorganic compound or a polymer or a hybrid, so polymer inorganic material. And many people try this, and this research faces also challenges, of course. But the hope is that overall we can reach higher energy density with these batteries, better safety, and also you will require new manufacturing technologies. And there's, of course, a new opportunity for new companies, new startups, to really generate a new technology by simply looking at new manufacturing possibilities. So let's have a look at some examples. And what I would like to show you is the example of copper sulfide. So in my group, we look a lot at so-called conversion reactions. So this can be all kind of binary, let's say, oxides or sulfides, and we're trying to use them in solid-state batteries. And very often you think this is a bad idea because these so-called conversion reactions, they suffer from a large volume expansion during cycling. But I want to show you here on this slide that actually quite a decent behavior is possible for some of these compounds. And copper sulfide is really a special solid-state special material that surprisingly works well in a solid-state battery. So I wrote here actually also some specifications of our cells. So we really try always to work with reasonable loadings. So the electrode has a theoretical capacity of around 5 milliamp hours per square centimeter. And we also don't use actually too much of solid electrolyte in our battery. So we try to use just 30 weight% in the cathode, which is quite a reasonable value, I would say. And you can see this is actually a charge and discharge curve at C/10. And this is actually the conversion reaction of lithium with copper sulfide. And you can see this is also a highly reversible process. The very special aspect of this reaction is that the end product here, this is copper. And for conversion reactions, usually you form nanoscopic particles. And in this case, actually, you form really macroscopic particles and crystallites. And this is shown here. This is a cross-section of our cathode after discharge. And you can see you have really a copper network, and the particles are very large, several micrometers in size. And for this reason, this reaction is called a displacement reaction. So it is a conversion reaction, but a special one. And this is the correct term for it is the so-called displacement reaction. For sodium, this doesn't work as well, so that's why I don't show the results, but so far we were not able to obtain competitive results for sodium in this case. This is an example for molybdenum sulfide. So here we have a comparison between lithium and sodium for liquid cells and for solid state cells. And the ideal reaction looks like this. Okay, so also very simple. You have molybdenum sulfide, and during discharge you form lithium sulfide and molybdenum, or sodium sulfide and molybdenum. The truth is that actually here in between there's a lot of intermediate compounds, and this reaction as written here does not really take place. This is really an idealized way of writing it. The good way about it is that you can use these equations to calculate energy densities, theoretical voltages, and so on, and the results are shown here. So if you assume this reaction, then you will have 1.55 volts for lithium and 1.16 volts for sodium. And here you can see some other specifications. So the capacity would be very high, of course, but this would be the voltage. And 1.16 or 1.55 volts is kind of like something you're not super happy with. It could be basically maybe an anode material for special applications, but in principle, the voltage is too high for an anode and too low for a cathode. But it's a very nice model system to study actually a comparison between liquid and solid state cells. So you can see actually the difference between lithium and sodium is 0.39 volts. And the difference originates simply from this difference here. So you can see here, this is again the reaction for lithium and sodium. And if you just build the difference, then this would be the difference between both reactions, right? So lithium reacting with sodium sulfide to form sodium and lithium sulfide. And from this, you can calculate delta G. And delta G relates to a difference in the cell voltage of these reactions, and 174 kilojoule per mole correspond to 400 millivolts. This is exactly the difference that you have in theory between both reactions. You can do this calculation actually not only for sulfides, but also for hydrides, oxides, and so on. So if you look at oxides, for example, the lithium version of the cell would be always almost 1 volt higher. So you can see this in metal air batteries, for example. For sulfides, also the lithium version gives a higher voltage. So it seems that lithium always gives a higher cell voltage. But you could see for chlorides, there's no difference between lithium and sodium cell in voltage. And if you would go to conversion reactions with bromides and iodides, then the sodium cell would have a higher voltage compared to the lithium cell. So this is actually counterintuitive. But indeed, actually, sometimes sodium cells can have a higher voltage compared to lithium cells. Yeah, here are the voltage profiles for our cells with liquid and solid electrolyte. And I think I have to speed a little bit up. So Ivana, if I take too long, please interrupt me. But I will try to speed up a little bit.
Still a couple of minutes.
Okay. Yeah, these are voltage profiles. So what you see here in a dashed line, these are liquid electrolyte cells for lithium and for sodium. And the continuous line are the solid state cells, also for lithium and for sodium. And what you can see here in both cases is cells with liquid electrolyte, they have always a higher capacity, right, because of many, many reasons. But you also see that the initial Coulomb efficiency of cells with liquid electrolyte is much lower compared to solid state cells. So in this case, actually, the initial Coulombic efficiency in the solid state is better. And therefore, it might be actually quite a good idea to switch to solid state cells, although you lose a lot of capacity, right? But the initial Coulomb efficiency is much higher. And what you also can see is that if you compare lithium and sodium, the capacity in case of lithium is always a bit higher compared to sodium, very likely because of more sluggish kinetics in the case of sodium. But for sodium, we found that if you go to slightly elevated temperatures, then you can have a much higher capacity. And this is always a good sign because kinetic limitations are something you can try to improve. If it would be a thermodynamic problem, then you usually have no not really an option to get an improvement, right? But kinetics is something, as a chemist or electrochemist, there are ways to tackle that. All right, so the last example I want to show you is we go on the anode side of a solid-state battery. So we look now actually on the molybdenum sulfide electrode. In this case, this is really the cathode. These were the solid electrolytes that we used, so LPS or NPS. And what we used on the anode side was lithium-indium alloy or a sodium-tin alloy, depending on what cell we look at. And the lithium-indium electrode is something we had a closer look at because many people use it, but the behavior of lithium-indium as an anode material is not really well understood. And this is a study we also published recently in Batteries and Supercaps. And this is now all about a phase diagram. And phase diagram always look very complex, but they contain very useful information. And what you see here is actually quite a nice example of how electrochemistry relates to phase diagrams. So this is a temperature axis. This is the phase diagram for indium, so pure indium on the left-hand side and pure lithium on the right-hand side. And when you start now lithiating indium, you start here and you move this way through the phase diagram. So you put more lithium in, and at some point you hit a line, and this means you have a phase transition. So in this case, you form an intermetallic phase. And then again, you come into a two-phase region, and then you hit again an intermetallic phase, and so forth. And you can always monitor the electrode potential during this experiment. And you can see here, as long as you're in this two-phase region between this indium-1, lithium-1 alloy and the pure indium, you have a very constant voltage at around 0.6 volts. And if you go further, then the voltage drops. Okay, so you can see how the phase diagram directly relates to your redox potential. These are the underlying measurements. So we obtained these results with relaxation measurements. And indeed, actually, we found at room temperature the equilibrium potential of the lithium-indium electrode, as long as you're in this part of the phase diagram, is 0.6 volts. And if you go too far, so if you assemble your counter electrode with too much lithium and too little indium, then maybe you might end up here, and then your counter electrode has a much different voltage, right, or even 0.1 volts. And then you get actually a wrong interpretation of your battery results. And at the same time, the lower you go, the more actually the driving force for side reaction increases. And this is something that is quite important in solid-state battery research. So if you have a bad interface with your anode, you get a very poor performance. And this is just a slide that shows you when you are in the right region. So you only have, let's say, indium-1, lithium-1 as a counter electrode. You're in the two-phase region, then you have a very stable plating and stripping of your solid-state cell. And if you put too much lithium into your indium electrode, then you have a rapid increase in resistance, so in impedance, and therefore your battery performance will be very bad. So always when you assemble these cells, try to remember that you should not put too much lithium onto your counter electrode, otherwise your experiment might go wrong. Yeah, with this I would like to close this little overview on sodium-ion batteries and solid-state cells. Of course, I want to thank the people that support our research. I want to mention these two papers that we recently published in Batteries and Supercaps. And if you have questions, of course, I'm happy to take them and hopefully answer them in a good way for you. Thank you very much.
Okay, thank you very much, Philipp, for the very insightful presentation. I really appreciate it a lot, like the discussion on the differences between lithium and sodium. You know, it's common knowledge that some people think that sodium is simply a bigger lithium, but there are very interesting differences between the system. So we have a couple of questions that I would like to start with from the attendees. So the first one is a very specific one, which was referring, I believe, to the graphite cell, which was cycled at 100 C. And there is a question about the loading of these kind of electrodes. And
So this is something, of course, one always has to keep in mind, because if you make electrodes very thin, then the rate capability becomes better, right? For this specific sample, I think we have the thickness was I think 80 micrometers. And the loading in milligrams per centimeter, actually, I don't know by heart, so I would need to look this up. But it's likely mentioned in the paper, because we always do this because we know about this issue, right? So there are a lot of ways to optimize rate performance, if you just tailor the porosity of materials. Sure. But indeed, the main message of this graph was that the diffusion coefficient is really high. So theory has shown that the solvated ions diffuse faster in graphite than lithium ions, and that's actually quite interesting. So there's a lot of mobility.
And since we are talking about this, I take the chance to ask a personal question, maybe. So you were discussing about the breathing effect, you know, when these big solvated ions enter into the graphite and then go out, there is kind of a breathing effect of the electrode. I was wondering if you ever investigated the Sei stability on the graphite in this case, and what's your opinion about that, or a comparison with the lithium system?
Yeah, so basically there are two thoughts, and it's probably some people that believe that there has to be an SEI, and some others that believe that an SEI is not needed. So, and I think also something that we learned also cooperating with you and your group in Ulm was that, I mean, SEI is very difficult, and if you have a binder in your electrode, this of course spoils very often any SEI analysis, because the binder can be very dominant in your XPS spectra. We did a lot of efforts in trying to characterize graphite electrodes without any binder, and we have no indication for an SEI. We also do not have an SEI using these operando DEMS measurements. So there's no evidence for SEI, and there are two publications out that claim that there's an SEI, but actually they use electrolyte that decomposes a lot. So they have an irreversible capacity of I don't know, I think 50 or 60 milliamp hours per gram. So of course, if you take certain salts that decompose, then you form an SEI. Also, then it's still not clear whether it's an SEI or not, because you don't know whether it's really a real SEI or maybe just a surface deposit. But finally, I just want to mention that I think there's no SEI for the simple reason because the reaction is super fast. And I think it's impossible to transfer a solvated ion at such a high speed into a graphite lattice if there would be an SEI. That's my personal opinion.
It's a very interesting conclusion. Look forward to your future studies and that. And there are other couple of questions that I have here. So someone is asking why the first irreversible capacity is so important in sodium cells. Most of the cells undergo a formation process before starting the real cycle. So why to focus so much attention on the first irreversible capacity? What's your opinion on that?
Okay, so this is basically, I would say, it becomes relevant in practical devices. Right, so in research, usually you don't care because your counter electrode is lithium or sodium, and you have unlimited supply of ions, so to say, or of sodium or lithium metal. In a full cell, all the alkali ions have to be supplied by the counter electrode. And if you have a too high irreversible capacity, this means that too much lithium or sodium is irreversibly trapped in your electrode and is missing for all forthcoming cycles. And the only way around this is that you oversize your counter electrode, and this means extra weight and extra cost. So you need to make sure that your Coulomb efficiency on both electrodes, so this is not only the anode but also the cathode, should be as low as possible.
Yeah, that's very interesting. And there are many questions here. Maybe later we will have also the chance to reply to all our attendees in the chat. I guess you have access to the attendees chat. But one last question is related to the differences in the solid electrolyte interface and the cathode electrolyte interface for lithium and sodium state batteries. Do you have any opinion on that? Like, what's the biggest difference and what are the main challenges in the case of sodium?
Between liquid cells and solid state cells?
No, sorry, lithium and sodium cells.
But but with liquid electrolyte, I guess. Yeah. That's of course a very long story, I guess. I cannot completely answer this. So the SEI formation is not the same, right? Because you have different conductive salts and you have a different redox potential where you intercalate your ions, lithium or sodium. What is the same is the solvent, right? Or you can choose to take the same solvents. But many people do, of course, and they work. But I think a good electrolyte is usually governed by additives, and they might not be always the same for sodium. I think this is something that still needs to be clarified, and there are studies on that. But one issue is that in sodium-ion battery research is that we don't have the high purity salts that we have in case of lithium. So when you see a poor performance for sodium, it might be also simply an impure conductive salt. And we have a lot of issues also when buying chemicals, that sometimes the purity is not as good as stated on the package. So this is a drawback right now in sodium-ion battery research. So purity really matters, and all the rest, I think, still needs to be properly discovered.
Totally agree. One very last comment on solid-state batteries. There is a question on how did you look into the sodium and the lithium-ion diffusion in your solid-state cells, and how did you really investigate the transport?
What we do is just standard testing. So we look at rate capability tests. And if you want to really determine physical chemical parameters like diffusion coefficients, that's super tough. I mean, of course, you can make these relaxation measurements. But what happens in solid-state cells, I mean, there's so many effects coming into play. It's, I think, right now quite difficult to make these measurements properly. So we didn't look at this yet in detail. Some other people do. I mean, also theoreticians do, of course. But there's, I think, a lack of data. So also here, if you have good ideas, this is something to look at, I think.
A nice area of investigation, yeah. So I think that to respect the time, I think we can thank Philipp and the great presentation. And Philipp, if you want to give a look at the attendee chat and take some time to reply to the many questions you got after your nice presentation, I just have to pick up some. So okay. Thank you very much again.
Yeah, thank you all. Bye-bye.
Okay, so it's time for the second speaker. Okay, here it is, Nagore. So we have here Nagore Ortiz-Vitoriano from CIC energiGUNE in Spain. She's gonna deliver a presentation on towards better understanding of sodium-oxygen batteries from material selections to electrolyte solvation. I will briefly introduce Nagore. So Nagore is a Knickerbocker Research Fellow who has been spearheading metal layer research at CIC energiGUNE in Spain since 2016, of which she became a research line manager in 2018. She obtained her doctorate in 2011 for her work on solid oxide fuel cell at the University of the Basque Country, UPV-EHU in Spain, and during the course of which she undertook research stay in DTU in Denmark, at the Imperial College London in UK, and she was awarded a doctoral special prize by the UPV-EHU for the significant contribution to experimental science. In 2013, she was awarded a Marie Curie International Outgoing Fellowship from the European Union, which enabled her to join the Department of Mechanical Engineering at the Massachusetts Institute of Technology in Cambridge in USA, where she worked with both lithium and sodium-air batteries. In 2015, she continued the fellowship at CIC energiGUNE, where she conducted also research stays at Oak Ridge National Laboratory in the USA, Deakin University in Australia, and Chalmers University in Sweden. So Nagore has focused on both rational design of electrode materials for energy storage, as well as fundamental research focused on elucidating the key processes in order to facilitate the rapid future development of both the material and at the system level. So I will pass now the mic to Nagore.
Okay, thank you.
We can see your presentation nicely.
Okay, thank you, Ivana, for the nice presentation, and thank you the organizers for giving me the opportunity to present the work we are currently developing at CIC energiGUNE regarding sodium-oxygen batteries. So Philipp already nicely explained the current energy outlook, how the energy demand is increasing every day, and we need new power sources with high energy density and high power density. Currently, we have everywhere lithium-ion technologies and are actually the hub for fulfilling many of the current demands. However, the energy density of these batteries is limited by the intercalation chemistry of the electrodes, and also there are many applications that we could use beyond lithium-ion technologies, as for example, sodium-ion for storage. So we can see here all the capacitors and the different battery technologies in one side, and then really high specific energy but low specific power in the case of the fuel cells. So there is a gap here, and this gap is met by the metal air batteries, which currently many of these batteries are being studied at lab scale. There is still a lot to do to become commercial. And today I will focus on the sodium air battery, which I'm going to explain the mechanism because it's quite different from Philipp explained before. In the case of sodium-ion batteries, we rely in intercalation chemistry. Here is more like a conversion reaction. We have a sodium-containing metal anode and sodium-containing electrolyte and their cathode, which normally is carbon. During this charge, what happens is the sodium is oxidized, migrates to the cathode, and at the same time at the cathode, the oxygen reduction reaction occurs, where the oxygen is reduced, and then combined with sodium to potentially form all these kinds of sodium oxides. And in principle, this reaction is reversible upon charge. So the main difference is that energy is stored in this discharge product. So the first study reported a sodium oxygen battery at room temperature was performed by Philipp Adelhelm and his group. And they saw nicely how you can discharge a battery and you can form these sodium superoxide cubes on the surface of that air cathode, which was analyzed by means of NMR and XRD to prove that it was this material, the sodium superoxide, and also some studied on Saclay. Here we can see that the charge of the potential is quite low, and this was what the first study showing that these batteries might be better on charge, unlike lithium-ion batteries already known until that time. But still, we have many challenges to overcome at the cell scale. So we have the same problems in the case of the sodium-ion batteries, which is the sodium reformation, and we have another problem in this case due to the oxygen. We have the oxygen at the air cathode, but normally the oxygen migrates until the sodium, which passivates its surface. In the case of the air cathode, it's really important to look at the design. We have seen that we have these big cubes, so we need a structure to accommodate them. And also at the cell chemistry, we will have superoxide, peroxide, and depending on which chemistry we have, then the performance is going to be different. And then the electrolyte, which is a protic in this case of batteries, we have many challenges to overcome that I will address. So that I will focus on the first parts of developing graphene-based air cathode. We are working within the graphene flagship project in order to develop a proof of concept sodium air battery. And also looking at the electrolyte, which are really important in this system because we have this superoxide in the solution that is highly reactive. So we really need a stable system. So we will look at the Kleins electrolyte and also some of the ionic liquids, and then the novel electrolyte that we just discovered for the sodium air chemistry. So the first part, in the case of the graphene, we already know that is really important, the cathode morphology. So it's not the same to have these carbon fibers where these cubes accommodate on the surface, or we have a really high surface area cathode. This is the case of carbon nanotubes that you can see that you can accommodate the discharge products all over the surface. So for that, we wanted to engineer 3D graphene air cathodes. And looking at the literature, we have only few studies looking at the graphene performance, but there was low cycle life, high over potential, and also looking at the mechanisms with Claire Gray's group, looking at the NMR, how we can monitor the reversible products while cycling. In our case, we synthesize two types of graphene. First, by the so-called Hammers method, where we can see here all the procedure to oxidize the graphite, and then to neutralize and finalize to get the suspension by washing, then filtrate and exfoliate. But this method is using really harsh reagents as strong acids and oxidants. And also, we always need a post-synthesis reduction step. So the second approach that we have followed is to exfoliate, electrochemical exfoliate graphite using a solution where you can intercalate these anions and the water, expand this graphite sheet, and then finally get this exfoliated graphene. When we are looking at processing, it's really important because these two methods, they are going to process in a different way. In the case of graphite oxide rod, it's really easy, for example, to have a suspension on water, but then we have the problem of all these functional grooves on the surface. So it requires a post-synthesis or a chemical or thermal reduction in order to get this defect or defect sites on the sheets of the graphene. In the case of the electrochemical exfoliation, graphene is not, we cannot disperse, as you can see here with the water, and there is the drawback of the need of using synthetic surfactants. And also really important when working with graphene is the restacking. These sheets tend to agglomerate, so we lose this porosity of surface area. So it's really important to engineer 3D structures in order to accommodate this discharge product in the case of sodium batteries. So the first study is looking at the Hammers method, and what we did is tune the porosity by changing the temperature. That means once we get that solution, we go to the freeze dryer and perform at different temperature so we can get different porosities. First was to get at room temperature. We can see that we can get a film. Then at minus 75 degrees Celsius, where you can get this kind of aerogel, and then at minus 196, where you can get more, like we say, more mesoporous-like material. We can see here that this increases the performance and the mesoporosity, and this increasing the restacking of the seams in the case of the film. And this we correlate with the electrochemical performance in a battery where we use sodium metal, we use an organic electrolyte, and this freestanding cathode. We can see that with the film we cannot even get any capacity, but then with the sample, which presents larger mesoporosity, we can get nearly 7 milliamp hour centimeter square at quite high rate if we compare with the state of the art. So we wanted to understand what the difference of these materials, and we look at the discharge product, and we found that the discharge products were really were the same sodium superoxide, which is this cubic morphology, but in the case of the film, we have only small cubes in some parts of the surface. Then when we go to this sample, we can find some of the cubes that they grow on the edges of the graphene sheets and some on the surface. And then for the sample which outperforms the other, we see the entire surface covered by this sodium superoxide, meaning that we have utilized all the surface area. We confirm this by NMR, that we have sodium superoxide, and also we found that these cubes preferentially grow in the graphene sheet edges or the lattice defects, which are more active. And we came up with this schematic, which explains why the difference in the cycling performance, because with the one freeze dry at minus 186, we can get a longer cycle life. And this is because in the case, imagine a film when you don't have porosity, the oxygen needs to diffuse. So the oxygen is that diffusion is going to be hindered. And if we block the active site for the oxygen is not going to be reduced or just in a small amount. That's the reason we only see some discharge product at really low capacity and low cycle life. Then when we go to the to the second sample, we can see that the diffusion is enhanced. You have some seeds that they are one on top of another, but the other forming like some kind of 3D structure. So in this case, the oxygen diffusion is enhanced, and you have this medium exposure of the active sites in order for the oxygen to be reduced. And in this case, we can increase this cycle lives to 20 cycles. In the case of the best performing samples, we have seen that this is really a 3D structure where all the graphene sheets, they are randomly oriented, and then the oxygen diffusion is easy. We can reduce it, and then we can form all this discharge product in the surface. So the critical parameters in terms of the cathode porosity, it will be to have in the mesosmall macropores, and the random orientation of graphene sheets is really important. But there is a problem that using this method is very tedious, it's a very aggressive process, and we need to do a post-synthesis method. So we wanted to go for a more environmentally friendly method and more sustainable. So we explore the electrochemical exfoliation of graphite using nucleotides. So these nucleotides, which is the adenosine monophosphate, is really nice because you have this aromatic nucleophase which interacts with graphene through the PP stacking, and also you have a phosphate group which is polar and can interact with water. Remember that I said before that the problem of the electrochemical exfoliation was not to have this a dispersion because of the water not interacting with this graphite, and we need surfactants. In this case, with a nucleotide, we can have this great interaction. So we have a dual functionality. We exfoliate the electrolyte, and we have a colloidal stabilizer, which facilitates the graphene processing in water. So first, what we did is just discharge this material in this electrolyte and with this condition using sodium metal, and we can see that the discharge capacity of the electrochemical exfoliated graphene is higher than the one of reduced graphene oxide. And surprisingly, the deposition mechanism is also different. In the first one, we have these big cubes on the surface of the graphene, but in the case of the electrochemical exfoliated graphene, we have these small cubes all over the surface, meaning that the mechanism is different. But when we went to cycling these batteries that we did to cycling to 0.5 milliamp hour centimeter square, we saw that the cyclability was really similar, a bit higher in the case of the RGO, and also that the potential on charge was increasing while cycling in the case of the EEG sample. And also we got some noisy voltage profiles. So we wanted to overcome this and increase this cycling performance. So what we did is we followed two approaches. First was to heat treat this sample in order maybe that there were many groups or functional groups on the surface in order to remove, to see if we could improve this performance, or basically to clean, to wash this material. Maybe the AMP content was too high that prevented the oxygen diffusion and the oxygen reduction or evolution reactions. So in this case, what we saw is that this clean EEG have really high discharge capacity. And we can see also that there is a different mechanism going from the one at temperature. Here you have 400, 800 to the one going to the clean sample. So meaning that we can have different mechanisms, more for one surface mechanism where you reduce the oxygen on the surface and then you grow this discharge product, to more solution mechanisms where you have all this sodium superoxide in solution, and once it reaches a supersaturating point, these cubes precipitate. So like this, we saw that the clean sample outperforms the other samples because maybe the quantity of AMP was too high before. And also we wanted to check the cyclability. Here you have the cyclability of reduced graphene oxide, where you have a 95% Coulomb efficiency, and you can see an increase on the charge over potential, but up to 300 millivolts when you cycle the battery for 70 cycles. If we go to the case of AMP, functionalized electrochemical spolitic graphene, we can see that we can perform 100 cycles, 30 more than in the case of RGO, but the bare potential in this case was increasing more rapidly to 900 millivolts at 100 cycles. And in the case of the heat treated sample at 800, there is loss of activity because the AMP, there is no more on the surface of the graphene. That is an SPS analysis that you can find in this publication. So basically, we can obtain this stable aqueous graphene bioins. We can really easily process this in the 3D graphene-derived structures by just using innocuous molecules as nucleotides in an environmentally friendly, cheap, and easy to scale process. So this was the first proof of concept using this EG electrode. And now we are currently addressing this high overpotential with other biomolecules in order to overcome this and to even improve the cycle performance. And also really important that we have proved that the multifunctional character of this nucleotide by spoliating electrolyte, colloidal stabilizers, and also possible catalytic nucleation effect during oxygen reduction and evolution reaction. Moving to the second part of the talk regarding the electrolyte formulation, we know, and Philipp before explained, that it's really important what is happening between the anode and the cathode. We have a solvated cation, in this case we have oxygen, we have all the interaction of the cation with the solvent and with an ion, and then the process which is the desolvation of this cation in order to form this sodium oxide. So in the case of sodium oxygen batteries, these are the most common used solvents, and we wanted to know and to understand what was the peculiarities of these solvents, because we know that they are only different in the oxygen groups, and as the glide chain increases, you also increase the chelating ability. So here we can see with the high donor solvent, what I say that we have this sodium superoxide solvated in solution, and then it precipitates out of the solution forming these cubes, or you could also have a surface mechanisms. That means that the sodium superoxide is formed just on the surface of your air cathode. This given higher discharge capacity for the higher donor number solvents. So then what we did, just like simple experiments using just commercial carbon papers, looking at low concentration and 2 rates, and looking at a higher concentration and 2 rates. And then we came up with this trend. We can see that here it follows the same trend, and here it differs. So we wanted to understand or to know which solvent is good depending on the characteristics of the batteries, or the energy density, current density. So what we did is to use a combinatorial approach. We really need to understand at the solvation energy, at the atomic scale, how the sodium is going to be surrounded, and how this sodium is going to interact with the solvent molecules, how this interaction. For this, spectroscopy is a really nice tool that we can use. And also, of course, the book properties as the ionic conductivity of the electrolyte or the viscosity. In the case of the first one, atomic, we already know the enthalpy of the solution, that the chelating ability of these 3 solvents is going to increase as we increase the solvent chain length. In the case of the tetraglide, we have 5 oxygens, and just this 5, with 1 molecule of tetragon, is able to solvate sodium by its 5 oxygens. That is going to be really highly bonded, and that's the reason when you go to high rate using tetraglide, we are not able to cycle the battery. And other really important to look at the molecular interactions. When you can get and inside, depending on the concentration, how these bonds are changing. So in the case of the oxygen evolution reaction, at this case, we look at the donor numbers to see if they can give us an insight. But in the literature, we can have different donor numbers, and it's really difficult just to follow this approach. So here we know that the desolvation energy of the BME, because it's less bonded, is going to be lower, and in the case of the tetraglyne, is going to be higher. And in this case, the glyne was a better solvent because it was a balance, the ability to solvate and desolvate the sodium, and also stabilize the sodium and superoxide in solution. And also here, related to the donor number, you can know which is the ability to solubilize that discharge product. When we go to higher rate, the performance of these solvents is really similar. We look at the viscosity, the diglyne viscosity in this case is higher, and here the electrolyte has less time to stabilize in the solution and form these ion pairs of the sodium solvent with the superoxides. And that might be the reason why higher rate is not really important, or this solvation or less important, because we can see that the performance is quite similar. We can also look really important how this solvent is coordinated around the sodium. This is what we know the steric hindrance. So we have in this case 3 molecules of DME giving a coordination of 6, or you can have 3 molecules of diglyne, but in the case all these oxygens, they do not participate in that solvation. So then you have some oxygens that they are free, and those they are going to be that molecules easier to desolvate when they reach the interface of the electrolyte cathode. So basically, depending on the system, you can have this kind of plot, and you can see which properties you need for your system in order to choose the solvent. And the latest study, just a few minutes, we say, what if we mix this diglyne electrolyte with the ionic liquids in order to overcome also the problems of glynes that they are toxic? So here we have a discharge also in a commercial carbon cathode with sodium metal, and we see that the glyne capacity is higher. Then we have the mixture, which is also quite good, and then with the ionic liquid, it's not able to discharge, probably due to the viscosity, because it's really viscous and the oxygen solubility is low. And surprisingly, what we saw is in the case of glyne, you can see these cubes randomly oriented of the surface, different sizes. But if you go to this mixture, you can see that you can have a really homogeneous distribution of these cubes along the surface, meaning that something has changed just by incorporating this ionic liquid into the glyne. The cubes are more smaller and uniformly distributed. Here you can see we also did 2 concentration in order to know which one was and to get an insight to the solvation. And we can see that in the case of the lower concentration, you can get bigger cubes, and in the case of the higher concentration, you can get smaller cubes. And we will explain why is this. First, one next thing about this electrolyte solution is that in the case of 16.6% mole sample, you can, even the Sei reactions are really low. In the case, if you go to higher concentration of salt, you start with these Sei reactions. So let's explain the different samples. In the case of 16, we have an excess of decline. This is the coordination. And in the case of the high concentration of salt, there is a deficiency of glyne. So this means that in the first one, you have free solvent, which is going to increase the solubility of sodium superoxide in solution, and hence the cube size is going to be bigger. And also, when you look at this is liquid and amount of the 2 solutions, we see that you have a more positive shift in the case of this concentration, meaning a stronger coordination ability. And that means that a larger desolvation barrier, which then implies a slower kinetics and leading to more uniform and also larger crystals. That's the reason we saw this difference in the morphology. Also, when we look at these species and how they coordinate, we have different possible scenarios, these three. So looking at the RDF and calculated coordination number, well, we saw that in the case of the lower concentration sample, we have sodium solvated by 2 molecules of lime in the mirror solvation cell. But we can also see that you can also have a contribution of the anion, but meaning that the main you have solvent separated ion pairs, which normally they are translated to greater diffusion coefficients and transport efficiency. If you go to higher concentration, you can have all these possible combinations, meaning that the anion is taking more part in that first solvation cell, and you can have all of these different contact between the solvent anion and the cation, and also that the coordination number decreases for the glyne and increases for the sodium TFSI. So this might be one of the reasons, the difference of these two materials. And you can get more insight in the special collection of Batteries and Supercaps that was just released. So just to keep in mind that the electrolyte design is really important. We change the deposition mechanisms, we change the kinetic, and we might change the performance. And finally, I would like to thank all the team at CIC energiGUNE, collaborators at the University of the Basque Country. In CAR, we collaborate with them in graphene, and with Deakin University in the ionic liquid and hybrid electrolyte, and all the funding agencies. And thank you for your attention.
So thank you very much, Nagore, for your very nice presentation. Okay, now we see you again. So there is a question on the first part of your talk, the one related to the use of 3D graphene air cathodes. And could you comment on the volumetric capacity and the mass loading of the graphene aerogel electrodes that you're working on?
Yeah, in the case of the graphene electrode, we are working in between 3-4 milligrams centimeter square per electrode. So comparing with what I said before with the state of the art, normally state of the art is below 1 milligram. So we try to go even twice or three times. In terms of volumetric energy density, that will depend on your cell design. And now we have really a small cell design, so we don't calculate, or we are not at that stage to calculate that energy density.
Sure, that's one of the difficulties of early stage technology. Yeah. So, and you did a very nice work on the electrolyte tuning and characterization. So you showed also in one of the slides, one of the nice graphs in which you show basically which are the most important properties of the electrolyte. So with all your experience, can you give us a suggestion on which is the best electrolyte solution you have ever worked with in terms of donor number, viscosity, the solvation energy, or the chelating ability, all the parameters that you have been studying?
Yeah, in terms where we work with glyne solvents, I would say D-glyne, because D-glyne is a bit more viscous than DME, but still is good, and it's not volatile. That's the problem with DME. Sometimes we have seen in some of the cells that you open and you no longer have that D-glyne. But the problem also with glynes that they are also working on, I believe in the case of sodium ion, is the toxicity. So we really need to find new electrolytes, and we are in the way of looking at a new liquid electrolyte similar to the glynes, but less toxic. And also this new hybrid electrolyte, just by adding this ionic liquid, is incredible because it was unexpected that it was going to be this nice homogeneous distributed. And so I would say that looking at this hybrid in this case of sodium oxide or even lithium air will be really important. And of course we are also working on making, and we have some publications with Deakin and Polymath on looking at ion gels, which is going to be key in the future to prevent all the problems of liquid electrolytes.
That's a very good answer. So there is another question here for you. I think that there are very nice comments on your presentation that you will maybe read in the attendee chat. I'm gonna go with the last question because we're running a little bit out of time. So how it was physically confirmed that the graphene is pure after the treatment with the nucleic acid that you used?
Well, the graphene composition we do it by XPS, but there is not going to be 100% pure, and it's not going to be one layer of graphene. There are few layers, 2-3 layers of the graphene. By SPS is how we quantify what we have on the surface of the graphene and how we did the study of the different treated samples of the clean. Here, that you can see a difference in the SPS. I would say that you can go to the small publication because there is a really nice explanation on that.
Very good. And maybe you can also share some of the references in the attendee chat.
Yeah, I will share them on the chat.
Well, thank you again for the nice talk.
Thank you,
I guess it's time to move on with the third speaker. Okay. So we're gonna have Giuseppe is with us.
Yeah.
Okay, so we are going to start with the multivalent battery session. We're going to have Giuseppe Antonio Elia here with us, and he's going to give a presentation on insight into the aluminum graphite dual ion battery. A nice introduction, a short introduction to Giuseppe. Giuseppe is currently a senior scientist at the Helmholtz-Institut Ulm. He received his bachelor in 2009, his master in 2011, and his PhD in 2014 from Sapienza University of Rome. During his research activities, he spent several years as a visiting scientist in highly qualified research centers such as Hanyang University, Münster Electrochemical Energy Technology, Argonne National Laboratory, and the Helmholtz-Institut Ulm. And he has worked also on many projects related to the development of advanced lithium-ion and lithium-ion batteries and beyond lithium-ion systems. So I will pass now the mic to Giuseppe. Maybe you can.
Thank you. Yeah. I can start the sharing. Yeah. You can see the presentation now.
We see the presentation, but not in presentation mode. And
yeah, that's fine.
Switch on your video if you would like to have us in your.
Yeah. Okay. Now it's fine?
Yes, that's perfect.
Okay.
Yes.
Thank you for the introduction, Ivana. It's a pleasure to be here and give this short speech about aluminum graphite system. Just a brief introduction of clearly, I believe that everyone knows why we are looking for a new electrochemical storage system. So the mission of the EU and if worldwide is to realize a climate neutral energy economy by 2050. And in this context, the battery technology and the electrochemical storage system is fundamental both for the electromobility, where lithium system have the main role, and for stationary energy storage, where the storage system are required to balance the energy produced by a windmill or a solar plant. And as already mentioned in the previous speech, lithium is the state-of-the-art and the most advanced battery technology. However, there are concerns related to the shortage of lithium, and in particular to lithium-related elements such as cobalt or nickel for the realization of lithium battery. And for that reason, there is much research is now dedicated to find an alternative to this lithium technology. And Several other elements has been investigated in the previous two presentations. The speech were mainly dedicated to sodium system, but also potassium, calcium, magnesium, and aluminum have been investigated in the past years to identify possible electrochemical storage system alternative to lithium. And in particular, aluminum is characterized by a very high volumetric energy density that is 4 times higher respect to lithium, and the main characteristic is the elevated earth crust abundance that make it potentially sustainable elements to be used for the realization of electrochemical storage devices. And to do that, we need to find we need an environment to utilize aluminum as an anodic material. We need to find an environment where aluminum can be easily stripped and deposited electrochemically. To do that, the electrolyte of choice are chloroaluminate melts. Here you can see one of the most used electrolytes for the realization of secondary aluminum batteries, that is the amine chloride, aluminum chloride. And using this kind of electrolyte is possible to efficiently strip and deposit aluminum metal. And one of the main advantages is that in this system, aluminum is not prone to form dendrite, similar to magnesium. And moreover, thanks to the elevated energy density, we need only a limited thickness or a limited volume of aluminum metal to obtain a reasonable surface capacity that is needed for the battery realization. Clearly, there are also several disadvantages in the use of this chloroaluminate melt. Most of it is related to the elevated reactivity of chloroaluminate melts, and here is a nice example is a manuscript recently published by Professor Guo, where it investigates the chemical stability of vanadium oxide, one of the most widely used oxide material for multivalent system, in aluminum chloroaluminate melt. And the study evidenced that the metal oxide is not stable in this kind of electrolyte, in this class of electrolyte, and that the electrochemical behavior generally attributed to the battery cycling and the aluminum intercalation, the intercalation is mostly due to the formation of soluble compounds that are electrochemically active. The reactivity also is fundamental also to beside the electroactive material to utilize stable and cell components, for example, metal current collector. This is also a great issue if you want to utilize this kind of chloroaluminate melt. And as an example here, is the reported electrochemical stability, the corrosion stability of several metals in this chloroaluminate melt environment. And we can see that even stainless steel is not stable to this chloroaluminate melt. This is a great limitation, in particular for large-scale system application. And to find to bring this kind of system to practical application, is necessary to identify suitable cell component. This is an example of a study we have done in cooperation with Sei about the screening of commercially available separator, commercial use for lithium-ion batteries. And from the preliminary screening, we have seen that none of these separator is suitable for the realization of batteries, because none of them is chemically stable in the chloroaluminate melt. Luckily, we found that the polyacrylonitrile is is stable in the chloroluminate melt. And in cooperation with Sei, we use an electrospinning method to produce non-woven membrane, utilize as separator in this chloroluminate melt. And as you can see from the electrochemical results of the stripping deposition process of a symmetrical aluminum cell, employing this electrolyte, we can efficiently strip and deposit aluminum with a limited overvoltage between the deposition and dissolution process. And consider that the overvoltage reported for this aluminum cell is close to the stripping deposition over potential reported for a lithium system in utilizing ionic liquid-based electrolyte. Clearly, the reactivity of the electrolyte used in aluminum system is one of the main issues. The second main issue is related to the identification of suitable positive electrode. And the main limitation in this case is associated with the high charge density of the aluminum ion and the limited mobility of the aluminum ion in metal oxide framework. This is, for example, a comparison of the diffusion energy required for the different ion, lithium, magnesium, zinc, calcium, and aluminum, to move in a metal oxide framework. In this case, is a vanadium oxide. And we can clearly see that for aluminum, the energy required is extremely high, making it unsuitable for battery application. For that reason, the research on aluminum system is in the past year is mainly focused on alternative chemistry, let's say. So like an ion intercalation or conversion reaction. In the following slide, I'm going to speak briefly about our activity in an ion intercalation process. When we speak about an ion intercalation, we speak about the utilization of graphite as positive electrode, and in particular to the aluminum graphite dual ion electrochemical cell that utilize aluminum metal as anode, this chloroluminate melt as electrolyte, and the graphite as cathode. This type of system has been firstly proposed in this manuscript, this famous manuscript by Stanford Group in 2015. And the reaction mechanism involved the intercalation of the anion, the aluminum chloride, in between the graphite layer. The graphite clearly is well known. Most of you know it as a nanode material for lithium-ion system, and however, the graphite is also capable of intercalating other type of anion or cation, also has through a multi-stage intercalation process. The multi-staging process can be easily followed by Operando XRD. This is a nice work done in cooperation with the research group at the Helmholtz-Institut in Berlin. You can clearly see that the reflection of the 002 reflection of the graphite upon charge process split with the formation of two new reflection associated with the formation of the graphite intercalation compound through staging. And by the following the evolution of the splitting of the graphite reflection, we can easily determine the staging behavior through the electrochemical process of charge and discharge. From the performance point of view, the fundamental and the most interesting characteristic of the aluminum graphite cell is the extremely high rate capability. Here we can see some cycling profile of an aluminum graphite cell using aluminum as anode and the graphite cathode and the ethyl methylimidazole as electrolyte. And the active material loading for this test is about 5 milligrams per centimeter square. And the rate capability of the system is extremely high, and we are able to obtain still 70 milliampere per gram with a current of 50 ampere per gram of active material. This means a full charge and discharge in 9 seconds. So this kind of systems has a performance close to supercapacitor. Moreover, one of the second great advantages of this type of system is the extremely high cycle life. Here you can see a cycling test of an aluminum graphite cell up to 50,000 cycles at 1 ampere hour per gram with a negligible capacity fading. And this test, the cycling test, is extended up to 500,000 of cycles with only capacity fading of the 30%. On the other hand, the reaction mechanism that involve an ion intercalation process in the graphite has a great limitation in the energy density of the system, since while for a rocking chair mechanism where the electrolyte acts as a medium, where the ion is shattered between the cathode and the anode, in dual ion cell, the electrolyte is directly involved in the electrochemical reaction, acting as a nanolite. For this reason, the electrolyte must be taken into account for the calculation of the energy density. And in particular for this kind of system, if we take into account the mass of the energy density of the system is a function of the concentration of the electrolyte. This is fundamental to properly determine the metric of the system. In fact, if we calculate the energy density of the system based on the graphite cathode only, we are out of scale, let's say. While to determine the suitable energy density, the proper energy density, we need to take into account the electrolyte mass. Hello?
Okay. Thank you, Giuseppe. Thank you very much for your nice presentation. Maybe you can stop sharing your screen if you like.
Yeah.
Okay, we have some very interesting questions for you. So maybe we can start from the last topic. You were discussing about the electrolyte consumption and the fact that we have to take into account electrolyte as an active material inside the dual ion cell. And the question is, do you need then to consider like eventually the refilling of your electrolyte in such a system?
Usually in, let's say, the main effect of the uptake of the electrolyte in the cathode is the limitation in the cell energy density, because it's expected that in a practical cell, is necessary to have an excess of electrolyte. So while in the conventional lithium-ion cell, the electrolyte is inactive, so the objective is to minimize the amount of electrolyte in the cell. A certain amount of electrolyte is required in this kind of system. For that reason, let's say, will be more easier to use an excess of electrolyte, so oversize the amount of electrolyte that you put in the cell, respect to use a refilling.
Very good answer. So we have another question actually related to the possible aluminum deposition and dendrite formation. So the question is, how could you circumvent the aluminum deposition inside the glass fiber separator? I guess this would be a nice question if we really had aluminum 3+, shelf
Yeah.
But I guess, can you comment on that?
Let's say for commercial purpose, glass fiber cannot be used. First of all, as a separator, because the thickness is too elevated and the mechanical properties of glass fiber are not suitable for a commercial purpose. And while the solution is to utilize a polymeric separator, so for example, the one proposed made on polyacrylonitrile.
That would somehow be able to circumvent the potential dendrite formation. And on the electrolyte system that you use in your dual ion batteries, so the acidity of the electrolyte is crucial there. So
yes,
there is a question on your amine chlorine and aluminum 3-chlorine electrolyte. You use a molar ratio of 1 to 1.3, because I guess you achieve a nice 1.5. So will it be more acidic if you would use a 1 to 1.3? This is the question. So what if you change the ratio and you go to 1.3?
Actually, in particular for the aluminum graphite system, since you deplete the anion, the energy density is a function of the concentration of the aluminum chloride in the electrolyte. For this reason, more aluminum chloride you can put in, better it is.
Yeah.
And more you put in, and higher is the acidity. So you form more this dimeric species, this aluminum 2Cl7.
Which is the species that then intercalates.
That is the species that guarantee the stripping deposition of the aluminum metal.
And have you ever performed any aluminum ions? Have you ever built any aluminum ion cell using manganese oxide as a positive electrode?
We tried, but the electrochemical activity at that time was very limited. And I will say now, especially if you want to obtain an aluminum 3+ aluminum ion batteries, you should avoid the use of this chloroaluminate melt, because clearly in this chloroaluminate melt there is no aluminum 3+.
Yeah, that would be the holy grail.
From the stripping deposition point of view, we are stick to the chloroaluminate melt, but from if you want to, ideally, we need to have a kind of chlorine-free electrolyte, where this will potentially solve the issue of the reactivity of the system, and also enable the possibility to use aluminum 3+ as a cation for the electrochemical process.
Very good. Now we have, maybe I'm going to just one last questions before we move to the next speaker. So there is someone interested in your very nice study that you did in collaboration with Helmholtz-Zentrum Berlin at BESI on the operando XRD measurement. They are asking if you could share with us some details on the cell setup that you use, and if you use a transmission or a reflection geometry.
The measurement was done with the white beam, so the beam was passing through the whole cell, and actually we were quite lucky because we use a cell configuration employing a Teflon and a glassy carbon current collector. But the choice was determined by the reactivity of the electrolyte. Additionally, we had a a further effect, because one of the problem when you use white beam is really energetic, and generally the cell heat up, especially if you have metal system. And we use this mini Svegelok because we have done it together with the XRD, also the tomography that have not been reported. Mini Svegelok cell with a 4 millimeter diameter that was possible to fit in the beam line.
That's very interesting. So there are a lot of other questions and nice comments on your presentation. Maybe you can take some time to answer into the attendee chat. And thank you very much. Thank you very much for your nice presentation. So then I guess we can move on with the next speaker. So Magali, okay, you're here. Maybe you can start sharing your screen in the meantime, and I would like to give a brief introduction for you. So Magali Gauthier is a researcher at CEA Saclay in France. Her interest includes alloy negative electrodes for non-aqueous magnesium batteries, interfaces, and post-lithium-ion batteries. Previously, after receiving her bachelor and her master degree from the University of Nantes and her PhD in material science from both University of Nantes and INRS University in Canada, she has been working as a postdoctoral associate at the Massachusetts Institute of Technology in the group of Professor Yang Shaorn in the Electrochemical Energy Laboratory, and she was investigating interfaces in lithium-ion batteries. So let me see if we see perfectly your screen and your title presentation. Please, Magali, the stage is yours.
Okay, thanks, Ivana. Thanks a lot for a nice introduction, and thanks to the organizer for giving me this great opportunity to present our work today. So my talk today will deal with the bivalent magnesium batteries and focus mostly on alloys-based negative electrode and their phase transformation upon reaction with magnesium. So first, few introductory words about magnesium and its properties. So despite a smaller potential of minus 2.4 volts compared to minus 3.0 volt for lithium, magnesium is a great alternative to lithium, as it can exchange 2 electrons instead of 1 for lithium. The main advantage of magnesium is its high abundance in the Earth's crust, which, similar to sodium, could limit the cost of these batteries in comparison to lithium-ion batteries. So magnesium presents actually a higher volumetric capacity than lithium, with a value of around 3,800 milliamp hour per cubic centimeter, in comparison to around 2,000 milliamp hour per cubic centimeter for lithium. And finally, we can say that magnesium 2+ present a smaller ionic radius than lithium, while in fact it carries 2 charges, which leads thus to low diffusion of magnesium ion in the solids. So the working principle of magnesium battery is similar to the one we've seen for lithium-ion or sodium-ion batteries, with an anode, cathode, and electrolyte. But the main challenge here in magnesium battery is that with conventional electrolyte, there's an incompatibility with the magnesium negative electrodes. In fact, when conventional electrolytes, such as carbonate, are in contact with magnesium metal electrode, there's the formation of a completely blocking passivation layer that inhibits an exchange of magnesium ion to strip or plate the magnesium metal electrodes. So to solve this issue, 2 main strategies can be envisioned. The first one is to develop and design new electrolyte solution. So I will not enter into the detail of this here, but we recently reviewed with Robert Dominko, Vito Ginotto, Romain Berthelot, this electrolyte solution here. And basically what I can say is there are some electrolyte solutions that are compatible with magnesium metal. They do not form any passivation layer, but the problem is that they are often corrosive and sensible to air, and they present a quite narrow voltage window. So another solution is to use p-block elements to replace the magnesium metal electrodes. So these elements form alloys with magnesium following this reaction. They are, for example, indium, tin, antimony, lead, and bismuth that have been mainly investigated first by Toyota and Bertolot's group. And they present capacity in the order of 2,000 to 3,000 milliampere hour per cubic centimeter and 300 to 900 milliampere hour per gram. So recently in this review, we tried to assess the capacity and the possibility of using these alloys as negative electrodes. So here we compare their energy density with when we look at a system with a negative electrode based on magnesium metal with 50% excess metal, and on an alloy-based electrode based on tin. And this calculation, note that they took into account both inactive and active material, binder, carbon, separator, current collector, except casing, and we also took into account the porosity of the separator and of the electrode in the case of the magnesium tin composite electrodes. So here are displayed the volumetric energy density as function of gravimetric energy density for different cathode material with this magnesium metal and this Mg2Sn electrodes. So as you can see, and as we can expect with this alloys material, we get lower practical energy densities than magnesium metal. And with this alloys, we also have two other challenges, which are similarly to lithium batteries and materials such as silicon or tin, a quite huge volume expansion upon a reaction with magnesium. And the second challenge is, as I mentioned before, the slow diffusion of magnesium ions in the solid in general. Yet there are many advantages of this alloy negative electrode that in fact counterbalance these drawbacks. So the main one is that this alloys material, they are compatible with conventional electrolytes, such as nitrile and glimes. They do not form any passivation layer, blocking passivation layer with this electrolyte. So they offer a way to extend the potential window of the magnesium batteries and thus to combine them with a high voltage cathode. Second, these alloys, they are maybe easier to produce than magnesium metal. We can produce them in the form of powder through, for example, ball milling or solid state synthesis. While if you think about a magnesium metal foil, for example, for a surface capacity of 1 milliampere hour per centimeter square, even if you consider an excess of 50% of magnesium, you need to produce a magnesium foil of around 4 micrometer, which may prove difficult to produce in a really clean way. And finally, the last advantage is as we have some powders, this can be processed in the form of slurries and composite electrodes with similar industrial processes that are currently being used in the lithium battery industry. So as I mentioned earlier, P-blocks elements have been looked at in the literature, mostly by the Toyota group and Bertolot group. We have indium, bismuth, lead, and this compound, they all alloy with magnesium to form compounds such as Mg3Bi2 or MgIn. So unfortunately, any of these elements here completely fulfill the requirement in terms of capacity, reversibility, or kinetic behavior. For example, if we look at bismuth, it really presents the best reversibility and the best kinetic behavior, but it has unfortunately the lowest capacity among all those elements. So one way to circumvent this is to combine these different P-block elements together to try to create a synergy that will help improve the global performance. So in literature, alloys such as tin antimony, bismuth antimony, or indium bismuth have been investigated. And in our case, in our group, we've looked at two new alloys, which are first the combination of antimony, which present a theoretical high capacity, with indium, which present a very low potential. So we combine them in the INSB intermetallic compound. And we also looked at the combination of indium with lead, which present a very low polarization and an interesting capacity also. So we looked at the INPB solid solution. So we will first take a look at the INSB intermetallic compound. So one thing that needs to be noted is that here the main challenge is in fact the irreversibility of antimony. So if you look at the reactivity of antimony alone with magnesium, it is able to react with magnesium to form the Mg3sb2 phase. But this phase is really stable, and the reverse reaction extracting magnesium from this structure is almost impossible. So this is the challenge we have to tackle here in the INSB intermetallic compound. So first, to determine if a synergy exists between indium and antimony in the INSB alloy, we compare a simple mix of indium and antimony with an INSB compound that we produce through ball milling. So here is shown the evolution of the potential as function of the number of magnesium 2+ inserted in the structure. Here we can see for a simple 1-to-1 mix of indium and antimony, only 0.6 magnesium 2+ are inserted in the structure, and we have a sol plateau around 60 millivolts, which in fact really indicates that we have solely the reaction of magnesium with indium, no reaction with antimony. In contrast, when you look at the behavior of the INSB compound, we can see that it is able to host close to 2 magnesium 2+ in its structure, which really show like here we have a synergy between the two elements. So the first magnesiation present two regions that are barely distinguishable, while the second magnesiation show two well plateaus. So the first region is in fact associated with the reaction of magnesium with antimony to form the Mg3sb2 compound, while the second plateau is linked to the formation of MgIN. So what is really interesting here to see is that this plateau here, this first plateau, corresponding to the formation of Mg3sb2, we can see it in magnesiation and in demagnesiation, showing that really the reversibility of antimony is here present, and that we indeed activated the reactivity of antimony when we combine it with INSB. So to evidence further the activation of antimony in this INSB compound, we wanted to determine the capacity, the proportion of the Mg3 of the capacity that is due to the Mg3sb2 compound. So to do so, we estimated the capacity on this plateau, and we reported for each magnesiation cycle here, with in green the capacity due to the Mg3sb2 phase, and in blue the capacity due to the MgIN phase. So you can see that on the first cycle, first magnesiation, Mg3sb2 seems to be responsible for around 42% of the capacity, and it accounts then of around 20% of the capacity after 20 cycles. So really on the quite long term, we've seen that the reversibility of SB is really activated. So to sum up, when in literature you look at the reactivity of antimony alone, Mg2+ can be inserted in the structure, but it's too stable for the Mg2+ to be extracted. But when antimony is combined with indium, the Mg3sb2 phase seems to be formed, and we can also partially remove Mg2+ from this phase. So let's look now at the phase transformation in this INSB compound. So from the electrochemical behavior, we expect, as we've seen, two biphasic regions, one corresponding to the formation of Mg3sb2, and one corresponding to the formation of MgIN at lower potential. So we wanted to see if we can confirm the formation of those phases. And so to reveal the phase form, we performed ex situ X-ray diffraction on different steps of the magnetization of INSB. So we start before cycling. So we have the characteristic signal corresponding to the INSB compound. Upon magnetization, when we insert close to 1 magnesium 2+ in the structure, we have, as expected, formation of Mg3Sb2. And we also see that some metallic indium is extruded from the structure, which is in fact similar to what has been seen before in the literature for the INSB reactivity with lithium. If we go further into the magnetization, up to 1.5 magnesium 2+, we still see formation of Mg3Sb2 and metallic indium. Finally, when we go till the end of the magnetization, interestingly, we can see some small peaks at 9, 12, and 16, close to 16 degrees that may correspond to the MgIN phase. However, one thing I want to highlight here is this was the only time that we've seen those peaks, and when we reproduce the data, these tiny peaks were not present. We will see it just after. So that means that at the end of the magnetization, we clearly see the formation of Mg3Sb2, but we see MgIN either in a really poorly crystalline state or even in an amorphous state. So as we've seen, the capacity that we obtain, the electrochemical behavior cannot be explained by the sole reactivity of Mg3Sb2. So this MgIN phase has to be here, and it's here in an amorphous state, which means that here we have an electrochemically driven amorphization of MgIN in the first magnetization. So to go further in the understanding of this crystallization, amorphization of the MgIN phase, we compared an electrode that we magnetizated, as seen before in the classical galvanostatic cycling. So here you can see no MgIN in this case. And we compared it with an electrode that was magnetizated with the GITT mode, where the electrode has time to reach a steady state and magnesium diffusion has time to happen. And in this case, after the GITT measurements, we can clearly see that the MgIN phase is here well crystallized, like really it's really occurring. So that means that when we are in a classical galvanostatic cycling, the MgIN phase is amorphous. But when the system has time to relax, to reach its equilibrium, the MgIN phase is formed in a crystalline state. So really, this electrochemical driven amorphization of MgIN is kinetically dependent. So to summarize quickly on the behavior of this micrometallic INSB compound, we confirmed those reactions that we were expecting with the formation of Mg3Sb2 and MgIN. But we showed that the MgIN phase is in fact formed here in an amorphous state. So the question now is why this MgIN is formed in an amorphous state. We can think about it in terms of energy barrier. So we start from an initial state to go through a final crystalline state. And to initiate nucleation and growth of the MgIN phase, the system has to overcome an energy barrier. This energy barrier is in fact dependent on both grain size and interface energy. And we have actually seen that while our ball mill INSB really seemed micrometric, interestingly, it has really small crystallite size in the order of 15 nanometer. So we can infer that we have a lot of crystallites and a lot of interfaces in between. That means that the energy barrier is maybe big in the case of the ball mill INSB, and that the system is not able to overcome this big energy barrier, and that thus the amorphization is preferred compared to the crystallization of the phase. So we've seen that the crystallization of this phase, MgIN, is depending on the rate, but also seems to depend on the starting material. So the question now is, can we tune those phase transformation by changing the particle size of and morphology of the starting material? So to answer this question, we produced INSB in a different route through a chemical reduction. And we obtain micrometric powder, but that is intrinsically nanostructure, and that is composed of a smaller particle than the ball milled material. But in the same time, that these individual particles present a larger crystallite size in the order of 80 nanometer, which we can infer will create less interfaces in the material. So now, what is the effect of this change in composition, in morphology, on the phase transformation? So in a similar way, we looked at ex situ X-ray diffraction data on different point of magnetization for this nanostructure INSB. And as you can see, we still see the formation of Mg3sb2 and indium. And interestingly, starting from the middle of the magnetization to the end of the magnetization, we clearly see the formation of crystallite MgIN here. So here, by changing the morphology of the particles and the crystallite size, we have changed the energy barrier for nucleation and crystallization, and this leads here to the crystallization of the MgIN phase. So in conclusion on this INSB alloy, we have seen that we've produced a new alloy for magnesium batteries. We show really remarkably that there is a great synergy between indium and antimony, which in fact allow us to partially unlock the reversibility of antimony upon reaction with magnesium. We have elucidated the reaction mechanism inside these alloys, and we demonstrated particularly competition between crystallization and amorphization of this MgIN phase, depending on both the rate and the size of the starting material. So let's now move quickly to the second alloy, which is the INPB solid solution. This is also another example of phase transformation in magnesium alloys. So in a similar way than INSB, we produce an INPB solid solution through ball milling, 5-hour ball milling of indium and lead powder. And this is what we obtain. So we really obtain coarse particles in the order of 200 micrometer. And consequently, we couldn't get any electrochemical reactivity from this particle. They were too big. So to scale down the particle size, we added a second step in the milling process by adding 30% in weight of carbon to help, in fact, limit the welding and melting of the INPB particles inside. So here is what we obtained. So as you can see, the addition of carbon really helps reducing the particle size by a factor of 20 to 40. And we get this INPB carbon composite, and we could get finally the electrochemical behavior of this INPB solid solution. So when you look at the evolution of the potential as function of the magnesium inserted in this structure, we can see that the first magnetization we can get close to 3 magnesium 2+ inserted in the structure, which is in fact expected if we take into account the formation of Mg2Pb and MgIN phase upon reaction with magnesium. So similarly, we check the phase transformation through ex situ XRD with this in this INPB carbon composite. So similarly, we looked at the phase form after the first magnetization. So as expected, we see the formation of Mg2Pb here, but interestingly, again, no MgIN phase here formed. So again, when you look at the capacity we get and the electrochemical behavior, the capacity we get cannot be explained solely by the formation of this Mg2Pb phase. So we infer that the MgIN phase is again formed in an amorphous state. Interestingly, in contrast to INSB, when we perform the first magnetization through GITT measurements where the system has time to relax and to reach an equilibrium, MgIN phase is not observed neither. So really, in the case of the INPB solution, this electrochemically driven amorphization of MgIN is here completely independent of the rate that we used. So we arrive finally to the conclusion. So I hope that I show you the complex phase transformation that can happen, occur in alloys for magnesium batteries. We have designed 2 new alloys, and in the INSB alloy, we have shown that we were able to really unlock the reversibility of antimony when it's combined with indium. In both INPB and INSB, we showed a peculiar electrochemical-driven amorphization of the MgIN phase that is really depending on the alloy composition, because this is seen here in INPB and INSB alloys, but that was not observed in the literature in pure indium electrodes or indium bismuth electrodes. And in the case of INSB, this amorphization is depending on the rate and also on the particle size and morphology of the starting material. So finally, one question that remains is how this phase transformation really affect the performance. Do they play a role or not on the performance of these materials? Finally, I hope that I convince you of the interest of alloys as negative electrode to replace magnesium metal. They are really compatible with standard electrolytes, and they could be one way to use a high voltage cathode. So finally, I would like to thank my team, and particularly Lucie Blondeau. This was actually our PhD work, A&R for funding. I have finally a small advertisement. We are actually hiring in my lab permanent research scientists that will focus on solid-state battery. So we invite you to propose a project and to apply. Feel free to ask me for more detail. And finally, I would like to thank you for your attention, and I'm happy to take any questions.
Well, thank you very much, Magali. This was a very insightful presentation. So I would like to start with a question. Actually, at the beginning, you were discussing the challenges of using magnesium and the passivation properties of magnesium. So you mentioned the 2 different approaches that generally are used. So either use corrosive electrolyte or your own approach, which is like substituting magnesium. So I was wondering which is, if you could share with us a few details on the cell and the electrolyte that actually instead you're using in your cells.
So actually, in our cells, so I say like there are some electrolytes that are compatible with magnesium, but they have a narrow voltage window. But in our case, we use this kind of electrolyte because it's easier to make half cells with magnesium. So we use this kind of Grignard reagent electrolyte. That was a way to quickly check the reactivity of our alloys. But we've tried recently to assemble like full cell with, for example, MgT-Fi in DME. It has been shown in literature. It works with bismuth. It works with tin. It seems to be a little bit more complicated with when you deal with the more complex alloys such as iron. But yeah, people show it's able to use like MgT-Fi in Glyme or nitrile. It works.
And we have a question also, like, what is your opinion on the possible use of solid-state electrolytes in magnesium batteries?
That some few people have started to look into it, but we're facing the same problems as any solids with magnesium. The diffusion is really slow. So when you work with magnesium, you have to be prepared to use
be patient.
But yeah, there are some people. Mostly people have also used the hybrid lithium magnesium solid electrolyte. Seems to work.
And the systems you prepare are very interesting. And there was a question on the way you prepare the ball milled phase of the indium antimony phase, and they were asking if there was any specific medium that you were using to avoid contamination during the ball milling process.
No, we actually simply mixed indium and antimony in stainless steel jars. So we have like a small contamination of iron, but really like in the order of 1 to 2%. So we were wondering if this could affect the performance, but it doesn't seem to. When we produce the INSB through the chemical routes, we've pretty much seen the same behavior. So this ionic particle are not affecting, but it was really an easy ball milling process.
It was a mild condition, and it was very interesting to see how the magnesium indium system was amorphous somehow, but you could not really detect it right directly. It was just a matter of calculation of capacity. So there is a question asking, have you ever confirmed the amorphous phase by using local structural probes?
Yeah, so we were really it was really puzzling, this MgIN phase. So we did some measurement to confirm it in the amorphous state. I didn't show the result here because they are not published yet, but we performed some X-ray absorption spectroscopy, and we've confirmed that the MgIN phase is indeed formed here in the amorphous state.
That's very nice. And there is the appearance of indium crystals from cathode is reversible, or it's like a limit of the composite, of your composite electrode?
This we have only seen with INSB, so I guess it's really material dependent. I guess it's the crystallographic structure that play a role here on this extrusion of indium that was also seen for lithium in the literature.
And now we have one last question, which is asking your expertise here, and it says, any suggestion on which electrolyte we could use for magnesium thin film batteries?
Oh, no idea. I'm really not the electrolyte expert here, so I guess people have tried. But
I know you work together with Robert, Dominko, and Vito Di Noto on a nice review paper, so maybe there are some good suggestions on electrolyte systems. Well, Magali, there are other questions which are very interesting. Maybe you could give a look at the attendee chat and reply to them. Maybe in the meantime, we go ahead with our last speaker.
Thanks.
Thank you very much again, Magali. So we have Robert with us.
Here.
Here you
here. Yeah.
Okay, while you start sharing your screen, I'm gonna give a brief introduction for you. So Robert Dominko is an employee at the National Institute of Chemistry in Slovenia, and he is affiliated at the University of Ljubljana. His research interests are in the field of material science and electrochemistry, and more precisely in the electrochemical system for energy storage, with main activities in the field of modern battery systems. He was a coordinator of 2 European projects developing lithium-sulfur batteries, and he has very tight connections with different industries. Currently, he is also strongly connected with the Battery 2030 Plus initiative and with Batteries Europe, and where he is one of the co-leaders of the task force preparing a strategy on the education level, which is very nice. His current research interests are different types of multivalent batteries. He is a deputy director of the European Virtual Research Battery Laboratory for Batteries, Alistair Airy, and he was awarded several awards, beside all of them the Honda Initiation Grant in 2013. And he is a member of the Slovenian Academy of Engineering. And today he's going to give us a presentation on possibilities and challenges of multivalent organic batteries. So thank you, Robert. We perfectly see your screen.
Thank you, Ivana. I hope everything is fine. And first of all, I would like to thanks editorial board of Batteries and Supercaps, and also editorial board of ChemElectroChem for this nice invitation and opportunity to, even in this difficult time, that we share our thoughts and our results on different battery chemistry, especially post-lithium battery chemistry that are coming. And during this talk, actually, there was a lot of discussion about sustainability, about sustainable approach using different type of post-lithium cations like sodium, aluminum, and magnesium. And here I would like to just to stress out also that organic batteries are actually offering us additional dimension of sustainability, since organic batteries are widely available, they are sustainable, easily recyclable also. And from this point of view, if we are really going to the era where everything will be electrified, what can be electrified, this part of science or this part of development will be also necessary, in my opinion. So as Magali showed some graphs that we actually built together beginning of last year, in the middle of the last year. And we wrap up everything in the nice review paper, which was published this year, at the end of last year. I would just like to stress out that organic batteries, actually, if they are combined with, for example, here with the negative metal with 50% of excess, they are offering still very affordable energy densities in terms of gravimetric energy density and also in terms of volumetric energy density. Of course, here we still have some issues to be solved, but at least thanks to Magali and her calculation with realistic condition, here we have just a nice picture that why it's worth to spend also some research time on this part of battery research. And so my discussion today, or my lecture today, will be mainly dedicated to use of different organic redox active organic moieties in 3 different type of batteries: in magnesium battery, in calcium battery, and in aluminum battery. And actually, organic batteries have a lot of possibilities, since they can be actually reacted, or they can be used with many different types of different anodes, and then their activity can be tuned by changing the size, changing the aromaticity, changing the groups, withdrawing groups, acceptor groups. So with that we can change also potential and specific capacity. But there are some disadvantages, like the major disadvantage is that they need to be polymerized, or they need to be grafted to some non-soluble substrate, which is actually not soluble in aprotic solvents that are typically used in this new type of batteries. And what I would like to stress out also, that it is highly recommended to use only N-type materials, since P-types need large excess of electrolyte, which then decreases energy density, and then such battery types usually they don't have a really commercial value or practical value. As Ivana said, we were awarded in 2013 with Honda Initiation Grant, where actually we proposed this magnesium organic battery as a possible solution for a new era of not only electromobility, but wider sustainability and lowering CO2 emissions and so on. And now in these 6-7 years that we are working on this topic, now we can already show that we can make a stack of 10 square centimeter large of anode and of the cathode, and this stack can actually light one LED diode which requires 20 milliamp current. And you can see here battery has a 2 volt, and everything actually is shown here, and it was published almost 5 years ago. So basically using some benzokinones we can obtain battery which has 2 volt which has 2 volt and which can run several cycles, and you will see later also several thousand cycles. But the question from the beginning was what is the mechanism? What actually is the driving force that for these charge transfer reactions? And do we have really interactions between quinone molecules and counter anions, counter cations, or do we have any different mechanism? So for this purpose, we have developed in operando ATR technique, where we can actually monitor the mechanism, what are the differences in the coordination of the organic polymers. So, and here actually in this part we can see that here or you can read in this paper that we don't have any interaction between the with electrolyte. We don't have any interaction with the housing of the cell, neither any of additives. So we can actually detect that this quinone group is activity is decreasing, and then during discharging and during charging is increasing back. So that means actually we are forming from quinone group, we are going to the quinonyl group, and then we are going back to the quinone group. What can be also done by subtraction of ER spectra from the beginning and at the end. And this is only first attempt that we were able to see the activity of these quinone groups. But nowadays we can also monitor formation of radicals. We can monitor some irreversible changes in the organic molecules and so on. So the major part, actually, it was the difference then that we found out between when we actually interact this quinone moiety with the lithium, or when we interact quinone moiety with the magnesium, because this quinonyl group was found at a different position. There was only 5 inverse centimeter difference, but already this 5 inverse centimeter difference made give a suggestion that there should be something different with the conformation of the anthraquinone groups. So here we show how actually anthraquinone groups are connected through the sulfur linker into the polymer. And then in lithium, actually, we have a monovalent lithium which actually coordinates quinonyl group. But once when you have a divalent magnesium, then there should be some kind of difference in the coordination, and that's what that actually that is shown with this 5 inverse centimeter difference. And that was also first suggestion that we really have a magnesium 2+ inside, and that we are using magnesium 2+, so we are using both electrons to coordinate 2 quinone groups, which are monovalent quinone groups. So here we need to be careful that actually cathode is still monovalent. But as we know that it's already known from the literature that magnesium, especially when you are working in magnesium chloride solution, typical our electrolyte is magnesium, it's mixture between magnesium chloride and magnesium TFSI. When you're working with that solution, there are many different species between. Actually, it's species between magnesium TFSI molecules, chloride molecules, not TFSI molecules, magnesium chloride and DME molecules. And those species are pretty much dependent on the concentration of chlorides that you have inside. So this gives somehow hint that Of course, there is a possibility that we might have also, for example, magnesium chloride plus, so monovalent magnesium complex, or even something different, which can be also inserted or coordinated in this organic moieties. But then this picture is even more complicated when you come to the interfaces. Then this actually distribution of species is completely different than in the bulk, and this part of actually this part of development is still unclear, and still needs a lot of experimental proofs and also computational calculations to actually understand a little bit better what is happening on the interface. But as we know that magnesium in chloride solution can be also monovalent magnesium chloride, we went into actually carefully, we inspect electrodes, and we did controlled experiment where electrodes were only soaked into electrolyte, and after washing we don't find any magnesium chloride inside. But once when they are discharged, actually you can see that magnesium ratio, this is weight ratio, is much higher than chloride, but still that gives us some hint that chloride is also co-inserted, and that we have some monovalent coordination with the monovalent magnesium chloride. And using some calculations, we actually can guess that approximately 75% of reduced quinone groups are actually coordinated with divalent magnesium, and 25% of groups are coordinated with monovalent magnesium. That's fine once when you are working in laboratory cells with a huge excess of electrolyte, but once when you are moving to the close to the commercialization, then each drop of electrolyte counts on energy densities. That means each microliter of electrolyte that is added is important, but also this gives us depletion of electrolyte with chlorides, and so we are still working to find the best combination between magnesium and chloride and TFSI salt, which can give us the best capacity. So there was then recently publication from United States group where they claim that using different salts, maybe this boron hexafluoroisopropyl compound can solve that problem, but we have recently published a paper in Batteries and Supercaps that this is not really the case, that even if you are using this type of salt, which is weakly coordinating which weakly coordinates magnesium cations, we can still find some HFIP inside the organic structure, polymer structure. So that means that still we have a co-insertion of magnesium, monovalent magnesium boron FIP complex. So then I would like to share also with you our knowledge about importance of electrolyte, importance of composition of electrolytes. Here's just one example working with anthraquinone molecule, and then this anthraquinone molecule is directly polymerized without sulfur linker to polyanthraquinone. And in lithium system, actually, you can see we can obtain very nice capacity retention, relatively good stability with some capacity fading at the beginning. And so capacity is around 220 at the beginning out of 260, which is theoretical capacity. But then moving to magnesium, you can see there is a huge difference according to the type of electrolyte that you are using. So concentrated TFSI chloride solution, then hexafluoroisopropyl material, it gives a really low energy capacity, and using aluminum added instead of TFSI, aluminum chloride instead of TFSI, actually it gives something in between, but with some capacity fading. But in this study, we have found also another peculiarity that adding aluminum chloride into the solution of the electrolyte, actually it increases it increases voltage, operating voltage. So you can see here that using this GITT, we were just curious where is the thermodynamic stability, or where is this OCV voltage, and the difference is like of 0.3, 0.4 volt, and this is significant difference, which is actually contributed by aluminum chloride, which actually shifts the electrochemical potential of the Quinone group. And then this electrochemical potential of Quinone group can be shifted again by designing ortho, para, meta positions and so on. So there is a lot of different area to play and to adjust, and of course then to bring this technology to the better solution. And here, as I said at the beginning, we were able to cycle this polyanthraquinonyl polymer for several thousand of cycles. In first 500 cycles, we had some faster drop of capacity, but then this drop of capacity was stabilized and until the all magnesium was not consumed completely. So that means but this capacity fading, as you can see, the voltage plateau was remained, but there was increase, and its capacity fading is mainly connected with the dissolution of the polymer. And of course, here we also need to be careful with magnesium because magnesium was consumed. That shows that this work, it has some practical possibilities, but still we need to work hard on that to protect interfaces, to design interfaces, and to improve cyclability. And as far since I am already discussing about magnesium, and it was said today that magnesium doesn't forming dendrites. That might be true. We don't have, or we were not able really to observe really dendrites, but of course magnesium is also metal which can be deposited back in a non-uniform form, and again it depends a lot on the electrolyte type. You can have like a flake type of deposition which still can grow through the separator, or you can have even some kind of needle type of deposition. For example, again, if in this MgCl aluminum chloride type of electrolyte, which then is much more dangerous because really this one can much faster grow through the separator and make short circuit. And if we have a soft short circuit in magnesium, that means that we need to reach several hundreds of degrees of centigrade before magnesium will be melted. In lithium, this is much lower temperature, so that means a lot of energy will be actually will be in the cell, so it's easily the cell can be ignited by fire. And how to explain this? We performed a study of interfaces which are stable interfaces and which are not stable interfaces, and it was reported that 001, this pinky interface, this is stable interface. But of course, once when you go to the faster kinetics, once when you go you want to work a little bit faster, also other interfaces are becoming active because polarization, because the potential difference between those two interfaces is not such huge, and then other interfaces are they don't allow homogeneous deposition, but they are more preferred like dendrite type of deposition. So that's actually shows another point which we need to be really careful once when we are designing magnesium battery. Now, in the second half of my talk, I will switch to the calcium battery. This is paper which was recently published, where we showed a reversible room temperature stripping and plating. And we have two papers actually out. One is with sulfur, one is with organic cathode. But today I will talk only about organic cathode, and that work was done in collaboration with University of Montpellier. So in calcium batteries for room temperature stripping and deposition process, we are using again this boron isopropyl hexafluoride salt. In this case calcium analog, which can actually, you can see here, we can have a nice reversible stripping and deposition at room temperature. But when we put this into the battery, again, here is anthraquinone. This time is PAX is linked with the sulfur. When we put this into the battery, we can obtain several cycles, very nice cycles, with some capacity fading. But then we observe a sudden capacity drop. And this capacity drop actually, if we just magnify this part of the electrochemical curve, we see here increase of polarization from cycle to cycle, and after 7 cycles, there is an increase of polarization is such high that it actually hits cutoff voltage, and that's why we have this sudden drop of the capacity. For that reason, we have established 3 electrode measurements of calcium organic battery in this particular system, and so in that case, actually, we can distinguish between the cathode and between the anode. And what we have observed that the cathode is working very nicely without problem, but actually the anode is causing a problem. So the passivation of the anode is increasing from the cycle to cycle, and after a few cycles, passivation on the anode is so severe that we cannot cycle anymore calcium. And this is only during the calcium stripping and not during the calcium deposition. So that means that there is accumulation of the degradation species from the electrolyte and formation of calcium fluoride on the calcium metal anode. So this shows that we have possibility to work at room temperature. Now there are 2 chances. Either we create some protection layer that will stop this continuous degradation of the electrolyte on the surface, or we need to develop new salts which will enable still room temperature reversible stripping and deposition, but without so severe passivation, or ideally without any passivation. And the mechanism of calcium actually coordination is exactly the same like we have observed, or I showed you in the case of magnesium. So also calcium coordinates and divalent calcium, then probably divalent calcium, because this phenolate group is approximately at the same position like in magnesium, while as I said, in lithium it is a few inverse centimeters lower position. And finally, I will move also to aluminum organic batteries. So this is a slightly different strategy that Pepe showed during his presentation. So, but using approximate very similar electrolyte system. Of course, this is one of the best system, and that work was done in collaboration with Chalmers University. Here, actually, we have connected aluminum electrode with organic cathode, and we have observed observed in the first cycle that we actually have a formation of 2 cycles, and that was not clear why we have then also in the 5th cycle, then in 10th cycle, but then in 20th cycle this actually lower voltage disappears. And just considering the voltage difference between lithium, magnesium, aluminum, we would expect voltage around 0.8 volt, not around 1.1 volt. So another question was, so the question was why we have this 300 millivolt shift, and also why we have 2 plateaus. And as you can see, actually the stability was pretty good for this starting experiment, but of course far away from something that can be used in some serious commercial application. And also the Coulombic efficiency, it's around, it's stabilized around 98-99%. So we again used FTR methodology, FTR operando mode experiments, and we studied that, but we did also one very simple experiment. We simply soaked electrode into the electrolyte for 24 hours, and then we assembled batteries with the non-soaked electrode and with the soaked electrode. And what we have observed actually that with soaked electrode, this lower plateau actually disappears, and we have only this higher plateau. So that means actually that aluminum chloride that is in the electrolyte, again, it has this withdrawing functionality on the quinone, electron withdrawing functionality on the quinone, and that increases the voltage. It's actually very similar as I showed in the case of magnesium when we added aluminum chloride into the magnesium electrolyte. And so this lower voltage actually is our quinone molecules that are not still affected with the presence of the presence of aluminum chloride, and this upper voltage actually are quinone molecules that are affected with the presence of the aluminum. And that was then confirmed also with the iris spectroscopy of the soaked electrode with the electrode that was pristine electrode and electrolytes. Actually, you can see that we have 2 different positions. So for pristine electrode and for the electrode which was soaked for the 3 days. So quinone IRI band for the quinone actually shifts to the lower wave numbers. Finally, I would like to also to show you our calculations and to give you a message out of that. So as Pepe said at the end of his presentation, quantity of electrolyte is important. And even though that we are using these organic molecules, we were able to detect also chlorides that was coordinating quinone groups. And the question was whether we have a monovalent or we have a divalent coordination. I can say we have something in between. So it's not monovalent and it's not divalent. It's a larger ratio of divalent coordination, but of course it's not trivalent. And now if we calculate how much of electrolyte we need to add if we have monovalent, and then also taking into account energy density of both electrodes, we can actually come out with a very low number of 44 watt-hours per kilogram for the full cell configuration. And this is not the same type of calculation that Magali did, and I showed this at the beginning, where porosity is taken into account, and separators, current collectors, and so on. This is only on pure material. Now moving to divalent coordination, this increases, of course, but still it's quite low, and so we need to improve this. But it's it's twice that it can be obtained with the graphite, maximum that can be obtained with the graphite. So that numbers show that there is a possibility to have something really attractive, but of course we need to come with some better cathodes and maybe also electrolyte, which will enable us at least divalent aluminum complex, if not trivalent alumina, pure alumina. And that brings me to the end. So I will just go quickly through these conclusions. So coordination cathodes have a great potential in multivalent batteries. So this is important. But low volumetric energy density might not be really suitable for premium electromobility, but might be suitable for some electric cars, city-driven electric cars. The solution of organic molecules for organic moieties is still a problem and needs to be solved. And as I discussed today, electrolytes have a great influence on organic moieties activity. So electrolyte composition and quantity, we don't know what is really going on the metal anodes, passivation of the metal anodes, morphology of the deposits, possible dendrites study. This is it should not be really omitted from the first hit that there are no dendrites. Okay, this is done. We should be very careful, and proper assessment of Coulombic efficiency. We might need also to reach numbers that are needed. We might go to the protection of metal, like we should do that also in lithium. And of course, there is a request also for new non-corrosive electrolytes and working on dissolution and shuttling of organic molecules that are dissolved inside the organic metal batteries. And with that, I would like to thank all my younger colleagues. All four, they finished a PhD in my group, and they are still working with me. So I'm really happy and to have them in the group. And also external collaboration from Patrick Johansson from Chalmers, Lorenzo Stevana from Montpellier, and I need to acknowledge also financial support, and also thank you for your attention.
Thank you very much, Robert. This was a very comprehensive presentation, going from magnesium to calcium to aluminum-ion batteries, organic type of batteries. And we have actually a question for you, and the speaker is asking, what is your opinion about using organic cathodes in aqueous zinc batteries?
This is another possibility which we don't work in our lab, but of course, again, you have this coordination reaction, and in aqueous zinc batteries, I think, or as far as I know, formation of dendrites on the anode is more problematic. But this is then if it's possible to work in more acidic conditions, then of course this is a really good solution. But I'm not on that field, so I'm not sure if this is really compatible or not.
I have another question for you, going back to your presentation on calcium batteries. I found very interesting the electrolyte, the boron isopropyl hexafluoride electrolyte, if the name is correct. You used it in combination with anthraquinone, and you observed the polarization effect, which actually is undesired. But that is a test that you got at room temperature, I believe, right?
Yes, all results that I showed are room temperature results, 25 degrees.
And how is that polarization affected by temperature? Have you studied that?
No, fortunately, we didn't study that. We stayed with the room temperature, but we were more focused on this increase of polarization during the cycling and this phenomena of passivation of calcium metal.
Understand. So we have another question on the aluminum part, on the aluminum batteries part. So the discharge is happening in some steps. So there was this step-like profile, and they are asking what is the reason behind it. If you could comment on that.
Yeah, these two steps, as I said, expected potential would be 0.8 volt. This is lower potential voltage, but then we observed this increase of potential for 300 millivolts, and this is correlated with the presence of aluminum chloride in the electrolyte solution, and actually withdrawing groups. So once when it's in close vicinity of quinone, actually it affects on the chemical potential, and with that on the electrochemical potential of the quinone, and actually increases potential. So this was observed also in magnesium. In magnesium batteries, if we add aluminum chloride into the electrolyte, we again observe 300 millivolt increase of potential.
That's very interesting. And there is a question back to the passivation properties of calcium. So the polarization effect was actually observed during the stripping process. Do you have any idea why the plating is not affected? Do you think the passivation layer is electric conductive but ionically insulating?
No, this is very good question. I would rather say that there are still some possibilities for plating, but I would only guess, and we need to go more in details to this study. What is the characteristic of passive film? It's a good question, but we don't have answer yet.
So there is still place for a lot of interesting studies in that area. We have another question, more generic, like what kind of separator did you use in these systems?
We are typically using glass fiber, but now we are turning more to the cell guard, or to similar separator that Celgard, but it's made by one company in Slovenia. So we are testing their separators. It's like electropolymerized, non-woven separator made of polypropylene. So it's a little bit more porous than Celgard, and a little bit more wettable also.
Okay. So I have a personal question actually from my side, because during the first part of the presentation, during the magnesium batteries part, and you had this very nice difference in between the magnesium 2+ coordination with your quinone and the magnesium chloride mono coordination. And you were saying that there was this difference in between 75 and 25% in the coordination, which of course changes a lot in the system and in the final performance. So have you thought or found a way to tune that and to go through the magnesium 2+? Only?
Actually, yeah, this paper that I showed, that different magnesium chloride DME coordination compounds are found in the electrolyte, and then they are found in the bulk of the electrolyte, and they are found also on the interface. And those compounds actually pretty much depend on the chloride concentration. So we are calling this Pourbet-like diagram, but Pourbet is it has potential and it has pH, and we have a voltage, and we have also chloride concentration. So it's like Pourbet-like diagram. But this study shows that there are maybe some possibilities to tune this, and also some experimental results really show that obtained capacity pretty much depends on the ratio between chloride and TFSI that we are using in our work.
That's very interesting. And is it like a similar effect to the increase in the voltage that you see by adding aluminum chloride in your...
No, it's just increasing the capacity. It's just increasing the capacity with, and that I think it's not proven from scientific point of view, but that's my opinion. I think this is due to the in coordination with, in some cases, more with divalent and in some cases more with monovalent magnesium.
Very interesting work. Well, I think we can thank Robert. There is going to be maybe some comments for you in the chat if you want to read those in the attendee chat. And I think we are at the end of our presentation, so maybe Rosalba can also join us again.
Yes, hi. Well, first of all, thanks to everyone. Thanks to Philipp. Thanks to Nagore, Giuseppe, Magali, and Robert for their really great presentations. Thank you, Ivana, so much for helping organizing, for helping finding the speakers, and also for moderating today. I think you've done an amazing job.
It's a pleasure.
Of course, thanks to our audience for asking so many interesting questions and engaging in the conversation, and also, once again, to the speakers that have spent so much time also answering all the remaining questions in the chat. I think this is a great engagement in the community. So before we go, I will like to ask you, so we want to continue to bring these virtual events to you, to the comfort of your home, but I would like to hear from you to see what other topics you're interested in. So my colleague Anne will now present a little poll. I hope you can see it so that you can answer what other topics you're interested in. So the ones that we have proposed are electrolytes for electrochemical energy storage, in situ and operando methods, also for energy storage and conversion, bifunctional electrocatalysis or electrocatalysts, organic batteries, electrochemical solar energy conversion, and molecular electrochemistry. So we will collect that information, and then from that we will get ideas for our next event. Okay, and before we go, I also want to remind you that we have a special collection on this topic, which I did not mention before, that this collection, I don't know if you can see my screen already. This collection is actually free to read for the rest of the month. So you should head there and check out the papers. Ivana and Philipp are some of the guest editors. And this is again joint between ChemElectroChem and Batteries and Supercaps. And if you missed it at the beginning, I also mentioned that if you click on this logo of Batteries and Supercaps on the on the top right of your screen, that will take you to the collection. And I also want to leave you an announcement for another virtual event from some of our sister journals, ChemPhysChem and ChemSystemsChem, on computational chemistry. And this will be on April 22nd. And here you can see the presenters, their presentation titles, and you can use this QR code to register, but I will also leave in the attendee chat the registration website. So with that, I'm going to stop sharing my screen. And I would like to thank you again. And please remember that you will get a link with the recording of the event. So if you had any technical difficulties or you missed part of the presentations, you can check those out later. And yes, if you want a certificate, just send an email to the journal email address. Thank you. Have a nice afternoon, rest of the day, evening, or night.